The universe is expanding into nothing, and that is not a metaphor. It is not poetic language designed to make you feel small. It is the actual, literal, testable truth about the reality you are living inside right now. Every second that passes, space itself stretches by thousands of miles in every direction. Distant galaxies are racing away from us faster than the speed of light. The edge of everything we can ever see sits 46 billion light-years away, and it is moving further with every breath you take. And here is the part that breaks your brain. There is no outside, there is no container, there is no void that the universe is inflating into like a balloon. Space is not expanding into anything. It is simply becoming more space, out of nothing, for no reason we can point to and say we fully understand. Physicists call this metric expansion. The rest of us call it impossible, because every instinct you have about how reality works tells you that if something grows, it must grow into something else. But the universe does not care what your instincts tell you. In 1998, two independent teams of astronomers discovered that this expansion is not slowing down. It is speeding up. Something invisible, something we have named dark energy but cannot detect or explain, is actively tearing the fabric of space-time apart at an accelerating rate. And the deeper we look with our most powerful instruments, the stranger it gets. There is a horizon out there, a boundary beyond which light will never reach us no matter how long we wait. Entire galaxies are slipping past that line right now, disappearing from our universe forever. So how does reality expand without an edge? How does space create itself from absolute nothing? And why does the answer to the most obvious question you can ask, what is the universe expanding into, have no answer at all? This is that story. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. The universe has no edge. That sentence should bother you more than it probably does right now, because embedded in those 5 words is a paradox so fundamentally alien to how your brain interprets reality that most people, when they first encounter it, assume someone has made a mistake. They haven't. The universe, all of it, every galaxy, every star, every atom, every point in space that has ever existed or ever will exist, is expanding. It has been expanding for roughly 13.8 billion years, and it is not expanding into anything. There is no room it is growing into. There is no container. There is no outside. Space itself is what is getting bigger. And if that statement just slid past you without friction, you're not paying attention. Because what that means, what it truly means when you sit with it long enough for the implications to land, is that the most basic assumption you carry around about the universe, that it exists inside something, is wrong. It does not. It is not in anything. It is the thing, and it is creating more of itself as it goes. When you blow up a balloon, the rubber stretches and the air inside pushes outward into the room. The balloon expands into space that already existed before you started blowing. That makes sense. You have a before state, a smaller balloon, and an after state, a bigger balloon, and the difference between them is volume that was already there waiting to be filled. The universe does not work that way. When the universe expands, it is not filling pre-existing space, it is generating space. The distance between two galaxies increases not because they are flying apart through a static background, but because new space is appearing between them. The galaxies themselves are not moving. The ruler is getting longer. Imagine you are standing on a grid, a flat, infinite plane with lines painted on it every meter. You close your eyes. When you open them again, the lines are 2 meters apart. Nothing moved. The grid itself stretched. You are still standing in the same spot relative to the lines near you, but everything farther away is now farther. That is what is happening to the universe at every moment. The grid is reality, and it is stretching in all directions at once. The human brain is not wired for this. For millions of years, our ancestors survived by understanding boundaries, the edge of the forest, the shore of the river, the walls of the cave. Everything that mattered had an inside and an outside. If you walked far enough in any direction, you hit something, a cliff, an ocean, the end of the known world. Even when we learnt the earth was round and you could walk forever without hitting an edge, the concept still made sense. You were walking on the surface of a sphere. That sphere existed in space. The space had to be inside something bigger, maybe the heavens, maybe an aether, maybe the mind of God. But something. There had to be something outside holding it all. There does not. The universe is not inside anything. It is the only thing, and for most of human history, we did not even know it was expanding. For thousands of years, the dominant assumption was that the cosmos was eternal and unchanging. The stars were fixed, the heavens were perfect. Aristotle taught that the universe had always existed and always would. The idea that it might have had a beginning, that there was a moment before which there was nothing, would have seemed absurd. Then in 1912, an astronomer named Vesto Slipher, working at Lowell Observatory in Arizona, started measuring the light from distant spiral nebulae. No one knew what those nebulae were at the time. Some thought they were gas clouds inside our own galaxy. Slipher found something unexpected. The light was redshifted. The wavelengths were stretched toward the red end of the spectrum, the same way the pitch of a siren drops as an ambulance drives away from you. The nebulae were moving, and most of them were moving away, fast. By the early 1920s, Edwin Hubble, working at Mount Wilson Observatory with a telescope powerful enough to resolve individual stars inside those nebulae, confirmed what they actually were: galaxies, entire separate star systems millions of light years away. And he confirmed what Slipher had found. They were receding. The farther away a galaxy was, the faster it appeared to be moving. In 1929, Hubble published a paper showing a linear relationship between distance and velocity. Twice as far, twice as fast. The universe was not static, it was expanding. That discovery should have been the most destabilizing moment in the history of human thought. It was not. Most people barely noticed. The stock market crashed later that year, and the world had other things to worry about. But inside the small community of physicists and astronomers who understood what the data meant, the implications were staggering. If the universe is expanding now, it must have been smaller in the past. Wind the clock back far enough, and everything, all the matter, all the energy, all the space itself, must have been compressed into a smaller and smaller region. Keep going, and you arrive at a point where the universe had no size at all. A singularity, a beginning. Georges Lemaitre, a Belgian priest and physicist, proposed this idea in 1927, 2 years before Hubble's paper. He called it the primeval atom. The idea that the entire universe erupted from a single point in an event of unimaginable energy. The term Big Bang would come later, coined mockingly by astronomer Fred Hoyle in 1949 during a radio interview. Hoyle hated the idea. He spent his career fighting it. The name stuck anyway. The Big Bang is not an explosion. That is the first thing you have to unlearn. When most people hear the term, they picture a bomb going off in empty space, a point of light and fire expanding outward into a dark void, debris flying in all directions. That is not what happened. There was no void. There was no space for anything to expand into. The Big Bang was the beginning of space itself. Before it, and that word before is already misleading because time did not exist either. There was no when, no where, no duration, no location. The Big Bang did not happen somewhere. It happened everywhere. Every point in the universe today was present at the Big Bang. You are standing right now in a place that was once part of the singularity. So is the chair you are sitting in. So is the air in your lungs. So is the most distant galaxy we have ever observed. All of it was in the same place, which was not a place 13.8 billion years ago. The expansion is not a movement of things through space. It is a growth of space itself. If you were somehow able to rewind the universe like a film in reverse, you would not see galaxies flying backward toward a central point. You would see the space between them shrinking. The galaxies themselves would not move. The distances would just get smaller and smaller until there was no distance left. Until there was no distinction between here and there. Until the concept of location lost all meaning. This is where language starts to fail. The question people always ask is the obvious one. If the universe is expanding, what is it expanding into? The answer, and this is not a dodge, this is not scientists refusing to answer because they do not know. The answer is that the question itself is broken. It assumes space is a thing that needs to be contained inside something else. It is not. Space is not a container. It is not a stage where events take place. It is a dynamic relationship between objects. When we say the universe is expanding, we mean the distances between objects are increasing. That is all. There is no exterior. There is no surrounding medium. There is no outside, because outside is a concept that only makes sense within space. And there is no space outside space. Think of it this way. Imagine the surface of a balloon again. But this time, imagine you are a two-dimensional creature living on that surface. You cannot look up or down. Those directions do not exist for you. You can only move forward, backward, left, right, along the skin of the balloon. Someone starts inflating it. From your perspective, every point on the surface is getting farther from every other point. The balloon is expanding. Now you ask, what is the balloon expanding into? The answer from your perspective as a creature confined to the surface is nothing. The expansion is not happening in a direction you have access to. The third dimension, the one the balloon is inflating into, does not exist in your reality. You can describe the expansion perfectly well, using only the geometry of the surface itself. You do not need to invoke an outside. Our situation is similar. We live in 3 dimensions of space, possibly more depending on whose model of physics you trust, but let us stick with 3. The universe is expanding. The distances between galaxies are increasing. If you ask what it is expanding into, you are asking for a 4th spatial dimension, a place outside our space where the expansion is occurring. That place does not exist, or if it does, we have no access to it and no way to describe it using the physics we know. The math works without it. General relativity, the theory Einstein published in 1915 that describes how gravity and spacetime are related, predicts an expanding universe naturally. You do not need to add an external container to make the equations work. In fact, adding one breaks them. Einstein himself did not believe it at first. When he saw that his equations allowed for a universe that could expand or contract, he found the idea so troubling that he added a term to the equations specifically to hold the universe still. He called it the cosmological constant. It was, he later said, his biggest blunder, because Hubble's observations a little over a decade later confirmed that the universe was not still, it was growing. And once that was established, the cosmological constant seemed unnecessary. Einstein removed it. 50 years later, astronomers would put it back when they discovered that the expansion is not just continuing but accelerating. But that is a different story. The point is this: the universe does not need an outside. It never did. The expansion is a property of spacetime itself. Space can curve, it can stretch, it can ripple. It is not a fixed background, it is a participant in the physics, and that changes everything. If the universe has no edge and is not expanding into anything, then it forces a question that feels almost childish but is actually one of the deepest in cosmology. Is the universe infinite? If there is no boundary, no edge, does that mean space goes on forever in every direction? Or is it possible for something to be finite and yet have no edge? The answer is yes to the second question, and the example is the same balloon we keep coming back to. If you are a creature living on the surface of a balloon, you can travel in any direction for as long as you want, and you will never hit an edge. But the surface is not infinite. It has a finite area. It is closed. It curves back on itself. You can circumnavigate it. The universe might work the same way, not in 2 dimensions like the balloon surface, but in 3. It is possible that space itself is curved in such a way that if you could travel far enough in a straight line, you would eventually return to where you started, not because you turned around, because space loops. That would make the universe finite in volume, but still without an edge. You could measure its size, but you could never find a place where it stops. The alternative is that the universe is flat or open, geometrically speaking, and that it extends infinitely in all directions. In that case, there is no total size. The volume is infinite. The number of galaxies is infinite. And somewhere out there, absurdly far beyond anything we will ever see, the same events that are happening here are repeating. Same atoms, same patterns, same version of you reading this exact sentence. Because in an infinite universe with a finite number of ways particles can be arranged, repetition is not just possible, it is guaranteed. We do not know which one is true. Current measurements suggest the universe is very close to flat, so close that if there is curvature, it is on a scale vastly larger than anything we can observe. That does not settle the question. A flat universe could still be finite if it has some exotic topology, some way of wrapping around itself that does not require curvature. Or it could be infinite. Both options fit the data, and both are uncomfortable. The idea that space goes on forever is hard to hold in your head for more than a few seconds before it starts to feel like a word you have repeated so many times it loses meaning. The idea that it does not, that it loops, feels like a trick, like someone has slipped a paradox into the rules and called it an answer. But those are the options. And the fact that we do not know which one is correct tells you how far we still are from understanding the structure of the place we live. What we do know is this: the part of the universe we can see, the observable universe, is not infinite. It has a definite size, roughly 93 billion light-years across. That is not a guess. That is a measurement derived from the age of the universe, the speed of light, and the rate of expansion. It is the maximum distance from which light has had time to reach us since the Big Bang. Anything farther than that is beyond our horizon, not because it does not exist, because its light has not had time to get here. The observable universe is not the same thing as the universe. It is the bubble of space around us from which information can reach us. Every observer in the universe has their own observable bubble centered on them. If you traveled 1 billion light-years to the left, your observable universe would be different. You would see galaxies we cannot see, and you would no longer see some of the galaxies we can. The bubbles overlap, but they are not the same. The full universe, the actual total universe, is something else, and we do not know how big it is. We may never know. So when people ask where the universe is expanding, the answer is not that we do not know. The answer is that the question is trying to smuggle in an assumption that does not hold. It is assuming space is inside something it is not. It is assuming there is a boundary there is not. It is assuming expansion requires an exterior destination. It does not. The universe is expanding into itself. Every point in space is moving away from every other point, not through space, with space. The distances are growing because space itself is being created, and there is no place that space is coming from. It is simply becoming. This is not an easy thing to accept. It runs against every instinct you have about how reality should work. But the data does not care about your instincts. The redshift of distant galaxies is real. The cosmic microwave background radiation, the faint glow left over from the early universe, is real. The mathematical models that describe how spacetime behaves under general relativity are real, and all of them point to the same conclusion. The universe is not in anything, it is the thing. And everything we thought we understood about edges, boundaries, and containers was built on a foundation that only makes sense at the scale of human experience. Step outside that scale, look at the cosmos as it actually is, and the foundation cracks. What replaces it is stranger, and in some ways more beautiful. Because if the universe does not need an outside, if it can simply be expanding and evolving and creating new space as it goes, then the thing we are living inside is not a place. It is a process, an unfolding, a structure that builds itself as it moves forward in time. There is no blueprint. There is no exterior scaffolding holding it up. There is only the universe doing what the universe does, growing, cooling, stretching, becoming, and we are inside it, trying to make sense of the rules, armed with instruments and equations and a stubbornness that refuses to accept that some questions might not have answers we can visualize. We have learned to measure things we cannot see, to describe geometries we cannot picture, to accept that reality at its largest scale does not resemble anything our ancestors could have imagined. The question is no longer whether the universe has an edge. It does not. The question now is what that means for everything else we think we know. And that is where things get truly strange. The observable universe is 46.5 billion light-years in radius. Diameter, roughly 93 billion light-years. That is the size of the bubble we live inside. The sphere of space from which light has had time to reach us since the beginning of everything. It is not the universe. It is our window into the universe. And that window, no matter how powerful our telescopes become, no matter how long we wait, will never open any wider than it already is. In fact, it is closing. Before we go any further, let us deal with the obvious problem. The one that trips up almost everyone the first time they hear these numbers. The universe is 13.8 billion years old. Light is the fastest thing in existence. Nothing can outrun it. If the universe began 13.8 billion years ago and light has been traveling toward us since then, the farthest distance we should be able to see is 13.8 billion light years. Not 46 billion, not 93 billion across. 13.8, maximum. End of story. That is what the math should say. It does not. And the reason it does not is the same reason the universe has no edge. Space itself is expanding. And when space expands, it does something deeply unintuitive. It stretches the distances light has already traveled. Imagine you are standing on one end of a long rubber sheet. A friend stands on the other end holding a flashlight. The sheet is 10 meters long. Your friend turns on the flashlight and the beam starts moving toward you at 1 meter per second. Simple physics says the light will reach you in 10 seconds. Now imagine that while the light is traveling, someone starts stretching the sheet, not pulling your friend farther away through space, but stretching the rubber itself so that every point on the sheet is getting farther from every other point. After 5 seconds, the light has traveled 5 meters, but the sheet has stretched. That 5-meter mark is now 7 meters away from you. The light keeps moving forward at 1 meter per second relative to the sheet, but the sheet is expanding underneath it. By the time the light finally reaches you, more than 10 seconds have passed, and your friend, who was originally 10 meters away, is now much farther. The light traveled the full distance, but the distance grew while the light was in transit. That is what has been happening to every photon that reaches Earth from deep space. Light left a distant galaxy 13 billion years ago when the universe was young and small. That galaxy was, say, 3 billion light-years away at the moment the light departed. The photon began its journey, moving through space at the speed of light, aimed in our direction. But space was expanding the entire time. By the time the photon arrives here, the galaxy it left is no longer 3 billion light-years away. It is closer to 30 billion light-years away, because space has been stretching the entire time the light was traveling. The photon covered the full distance, but the distance grew. This is not a violation of the speed of light. Light is still moving at exactly the speed it is supposed to, roughly 300,000 kilometers per second. It has not sped up. What happened is that the ruler changed length while the race was being run. Space itself expanded, and the expansion carried the starting line farther and farther away while the photon was in motion. When astronomers say the observable universe has a radius of 46 billion light-years, they are talking about co-moving distance. That is the technical term for the distance to an object now, accounting for all the expansion that has occurred since the light left. It is the current separation between us and the farthest objects whose light is just now arriving. Not the distance those objects were when the light departed. The distance they are now. The distinction matters because it is the difference between thinking the universe is the size of a room and realizing it is the size of a continent. When the light we see today from the most distant galaxies left those galaxies, the universe was much smaller. Space has expanded by a factor of roughly 3.3 since then, meaning every distance that existed back then has been stretched to more than 3 times its original size. A galaxy that was 10 billion light-years away when it emitted the light we are now receiving is currently more than 30 billion light-years away. We are seeing it as it was, but it is no longer where it was. Run that process in reverse, and you can start to see how the size of the observable universe is calculated. We know the age of the universe, 13.8 billion years. We know the speed of light. We know how fast space has been expanding at different points in the universe's history. Put all of that into the equations of general relativity, account for the stretching of space over time, and out comes a number. 46.5 billion light-years. That is how far away right now the most distant observable objects are, not how far their light traveled, how far away they currently sit. The light itself has traveled 13.8 billion light-years through space, but space was expanding while it traveled, so the source of that light is now much farther away than 13.8 billion light-years. The photon has been on the road for the entire age of the universe, but the destination kept moving. Here is another way to think about it. If you could freeze the expansion of the universe right now and somehow send a signal instantaneously to the most distant galaxy we can currently observe, that signal would have to travel 46.5 billion light-years to get there. That is the current physical separation. But we cannot freeze the expansion, and we cannot send instantaneous signals. So the light that left that galaxy billions of years ago is only now reaching us, and by the time it gets here, the galaxy has moved even farther away. In fact, it has moved so far that if we tried to send a message back, even at the speed of light, the message would never arrive, because space is expanding faster than light can cross it. This brings us to the edge of the observable universe. Not a physical edge, but a horizon. The cosmic light horizon. It is the boundary beyond which light has not had time to reach us yet. Not because the light is slow, because the universe has a finite age. There are galaxies farther than 46 billion light-years away, many of them, possibly an infinite number of them, but their light has not had enough time to get here. The universe is only 13.8 billion years old. Light from anything farther than a certain distance simply has not had time to complete the trip. That distance, when you account for expansion, turns out to be 46.5 billion light-years. Beyond that line, we go dark, not because there is nothing there, because the information has not arrived yet. Every year, that horizon expands, slowly. As the universe ages, light from slightly farther objects reaches us for the first time. The observable universe grows by roughly 1 light-year per year. You would think it would grow faster than that. After all, every year, light has 1 more year to travel. But space is also expanding, and in the time it takes light to travel 1 additional light-year toward us, space has stretched enough that the net gain is only about 1 light-year. The expansion is eating into the progress, and because the expansion is accelerating, driven by something called dark energy, the rate at which we gain new observable space is slowing. Eventually it will stop, and then it will reverse. But that is a story for later. The observable universe is not the universe. That sentence is worth repeating because it is one of the most important facts in cosmology and also one of the easiest to forget. When you see images from the Hubble Space Telescope or the James Webb Space Telescope showing galaxies scattered across a field of view, when you read articles about the number of galaxies in the universe, when you hear estimates like 2 trillion galaxies, that number is referring only to the observable universe, the part we can see, the part within our 46 billion light-year bubble. The full universe, the actual total universe, is bigger. How much bigger, we do not know. Current estimates based on models of cosmic inflation suggest the full universe is at least 250 times larger than the observable portion. That would make it roughly 7 trillion light-years across, minimum. Some models suggest it could be vastly larger than that. Others suggest it is infinite. If space is flat, which current measurements indicate it is, or very close to flat, then the universe likely extends forever in all directions. In that case, there is no total size, no number of galaxies, no edge, just space going on without end, filled with stars and galaxies and clusters and voids, repeating the same structures over and over because there are only so many ways matter can arrange itself, and infinity guarantees every possibility gets tried an infinite number of times. If that is true, then somewhere out there, impossibly far beyond anything we will ever see, there is another galaxy that looks just like the Milky Way, another star that looks just like the Sun, another planet that looks just like Earth. Another version of you reading these exact words, not because of magic or metaphysics, because in an infinite universe with a finite number of particle configurations, repetition is mathematically inevitable. Every possible arrangement happens, and then it happens again and again forever. We do not know if the universe is infinite. We may never know. What we do know is that the part we can see, the observable universe, is finite. It has a definite size, and everything beyond that size is, for all practical purposes, unreachable. Not just now, not just with current technology, forever. Even if we could travel at the speed of light, we could not reach most of the universe, because space is expanding faster than we can cross it. Here is the uncomfortable part. 97% of the observable universe is already unreachable. Even if you left right now, traveling at the speed of light, you could never get there. The expansion of space is carrying those regions away from us faster than light can close the distance. They are still visible because the light they emitted in the past is still arriving. But the objects themselves, the galaxies we see in those distant regions, are receding from us faster than the speed of light. Not because they are moving through space that fast, because space between us and them is expanding that fast. There is a sphere around Earth, much smaller than the 46 billion light-year observable radius, called the cosmic event horizon. It sits at roughly 15 billion light-years. Anything beyond that distance is not just far away, it is gone. If a supernova exploded right now in a galaxy 16 billion light-years away, we would never see it. The light would never reach us. Space would expand too quickly. The light would spend eternity trying to cross a gap that is growing faster than the light can travel. The photon would never stop moving. It would never slow down. It would just never get here. Running at full speed on a treadmill that is accelerating faster than it can run. That 15 billion light-year boundary is the edge of what is called the causally connected universe, the region of space that can still, in principle, affect us or be affected by us. Anything beyond that is severed, not by distance, by expansion. The universe has cut the thread. We will never receive signals from those regions. We will never send signals to them. They will never know we existed. We will never know what happens to them. The separation is absolute and permanent, and that boundary is shrinking. Every year, galaxies that were once inside the cosmic event horizon cross it and disappear from the list of places we could ever reach. The observable universe expands as new light arrives from farther away, but the reachable universe contracts as expansion accelerates. We can see more, but we can touch less. The view is getting bigger, the cage is getting smaller. If you could somehow stand outside the universe, which you cannot, and watch it evolve over trillions of years, you would see the observable universe from Earth's perspective gradually empty out. Galaxies near the edge of visibility would redshift into darkness as their light stretched into wavelengths too long to detect. Then galaxies closer in would fade, then closer still. Eventually, billions of years from now, observers on Earth or whatever remains of Earth will look out into space and see almost nothing. A few nearby galaxies in the local group, the small cluster of galaxies that includes the Milky Way, Andromeda, and a few dozen smaller companions. Everything else will have receded beyond the horizon. The night sky will go dark, not because the stars burned out, because space grew too fast. That is the future of the observable universe, not an explosion, not a collapse. A slow, quiet fading as the galaxies slip away one by one into the dark, still shining, still burning, still full of stars and worlds and perhaps even other civilizations looking up at their own skies and wondering why the universe is emptying out around them. They will never know we were here. We will never know they are there. Expansion will have separated us so completely that no information, no signal, no particle of matter or light will ever cross the gap again. That has already happened to most of the universe. The vast majority of galaxies that exist right now are already beyond our cosmic event horizon. We will never see them, not because they are too faint, because their light is being stretched by expansion faster than it can travel toward us. They are invisible, not due to distance, but due to geometry. The shape of space-time itself has locked them away, and yet they are out there, right now, as real as the Milky Way, as real as the sun, filled with stars and planets and dust and gas and perhaps life. Entire sections of the universe that are forever unknowable to us, not because we lack the tools to observe them, because the structure of reality makes observation impossible. This is what the 46 billion light-year radius represents. It is not a wall, it is not a boundary in space, it is a horizon in time, a limit on how far back we can see. Everything within that bubble is visible because light from those regions has had time to reach us. Everything outside it is invisible because the light has not had time to arrive yet, and much of it never will, because space is not standing still while the light travels. Space is stretching, distances are growing, and the farther away something is, the faster it is receding. The question people ask at this point is usually some version of the same thing. If we cannot see past the edge of the observable universe, how do we know there is anything out there? How do we know the universe is bigger than what we can observe? The answer comes from two places. First, the geometry of space. Measurements of the cosmic microwave background radiation, the faint glow left over from the early universe, allow physicists to determine the curvature of space. If space were curved like the surface of a sphere, we would see certain patterns in the microwave background. We do not see those patterns. Space appears flat, and if space is flat, then unless we are sitting at some special central location, which there is no reason to believe, the universe must extend far beyond what we can see. A flat plane does not end at the edge of your vision, it keeps going. Second, cosmic inflation. In the first tiny fraction of a second after the Big Bang, the universe underwent a period of exponential expansion. Space expanded so rapidly that regions which were once close enough to interact were flung apart faster than light could travel between them. The observable universe today is just one small patch of that inflated space, a single bubble in a much larger foam. The math of inflation predicts that the total universe should be vastly larger than the part we can observe. How much larger depends on how long inflation lasted, and we do not know that precisely. But even conservative estimates put the full universe at hundreds of times bigger than the observable portion, and many models suggest it is infinite. So when cosmologists say the universe is bigger than 46 billion light-years, they are not guessing, they are reading the data. The shape of space, the distribution of galaxies, the patterns in the cosmic microwave background, all of it points to a universe that extends far beyond the edge of our vision. We are not seeing the whole thing, we are seeing a small finite patch of something much larger, possibly infinitely larger. That should bother you. It should feel wrong that most of the universe is hidden from us, not because it is too far away, but because the rules of space-time make it inaccessible. It should feel strange that the thing we call the universe, the totality of existence, is not something we can ever fully observe or map or even conceptualize. We are stuck inside a bubble, watching light arrive from the edges, knowing that beyond those edges is more. More galaxies, more stars, more space, and we will never see it. This is the observable universe. A sphere 93 billion light-years across, centered on Earth, defined not by walls but by time. It is the region from which light has had time to reach us since the beginning. Everything inside it is visible, at least in principle. Everything outside it is not, and the boundary between the two is not fixed. It shifts, expands, changes as the universe ages and as space continues to stretch. Every year we see a little farther. Every year a little more of the universe crosses into view. But every year more of it also slips beyond reach, carried away by expansion into a region we will never be able to touch. The window is 46.5 billion light-years wide. It is the biggest window we will ever have, and it is not nearly big enough. But the size of the window is not the strangest part. The strangest part is what is happening to the glass. Because space is not just expanding, it is stretching. And that stretching is doing something to light, to distance, and to time itself that most people do not realize. Something that makes the observable universe not just large, but fundamentally different from the kind of space you move through every day. Space is not empty. That is the first thing you need to understand before anything else makes sense. When you look up at the night sky and see the blackness between the stars, your brain tells you that you are looking at nothing, a void, the absence of everything. Your brain is wrong. Space is not nothing, it is something, a physical structure with measurable properties that can bend, ripple, stretch, and tear. Einstein called it spacetime, 4 dimensions woven together into a single continuous fabric. 3 dimensions of space, up, down, left, right, forward, backward, and 1 dimension of time, past and future, all linked so tightly that you cannot have one without the other. Space is not the stage where events happen, it is part of the event. And right now, at this exact moment, it is stretching, not in one place, everywhere. Every cubic meter of space in the universe is expanding, getting bigger, creating more distance between the objects it contains, and it is doing this so thoroughly, so uniformly, that unless you are looking at galaxies millions of light years away, you will never notice it happening. The room you are sitting in is not expanding, the space between your chair and the wall is not growing. The distance from Earth to the Sun is not increasing. Gravity holds those structures together tightly enough that the expansion of space does not affect them. But step outside the bounds of gravity, outside the pull of stars and galaxies, into the vast intergalactic voids where almost nothing exists, and space is stretching so fast that galaxies on opposite sides of the universe are receding from one another at speeds that make light look slow. Some of those galaxies are moving away from us faster than the speed of light. That sentence should trigger alarms in your head. Nothing can move faster than light. That is one of the foundational rules of physics. Einstein proved it in 1905 with special relativity. The speed of light is not just fast, it is the speed limit of the universe. The maximum rate at which information, matter, or energy can move from one point to another. If you tried to accelerate a spaceship to the speed of light, you would need infinite energy. You cannot reach it, you cannot exceed it. The universe does not allow it. And yet galaxies are doing exactly that, receding from us at velocities well above 300,000 kilometers per second. They are not breaking the rules. The rules are more complicated than most people realize. Here is the distinction that matters. Objects cannot move through space faster than light. But space itself is not an object. Space can do whatever it wants, and what it is doing right now is expanding so rapidly that the distances between distant galaxies are increasing faster than light could ever cross them. The galaxies themselves are not moving, not in the way you think of movement. They are not flying through space like rockets. They are sitting still or close to still, relative to the space immediately around them. But the space between them and us is growing. New space is being created in the gap, and that process, the expansion of space itself, is not limited by the speed of light. Think of it this way. Imagine 2 ants sitting on a rubber sheet. The ants are not moving. They are standing perfectly still. Now someone starts stretching the sheet, pulling it in all directions. The ants are still not moving. Their little feet are planted in the same spot on the rubber, but the distance between them is increasing because the rubber is expanding. If you measured how fast the ants are separating, you might find that the gap between them is growing at 10 centimeters per second. That does not mean the ants are walking at 10 centimeters per second. It means the sheet is stretching at that rate. The ants are just going along for the ride. Now imagine the sheet is 1,000,000 kilometers long and it is stretching everywhere at once. Every square meter of rubber is expanding by 1% per second. The two ants are now so far apart that the total rate of separation between them exceeds the fastest speed any ant could possibly run. They are not running. They are standing still. But the sheet is stretching so fast that the distance is growing faster than any ant could cross it. That is what is happening with galaxies. Space is the sheet, the galaxies are the ants, and the stretching is so aggressive that distant galaxies are receding from us faster than light can travel, not because they are moving through space, because space is carrying them. Einstein's equations allow this. In fact, they predict it. General relativity, the theory that describes how gravity and spacetime interact, does not place any speed limit on how fast space itself can expand. The speed limit only applies to objects moving through space. A photon cannot travel faster than light. A spaceship cannot exceed light speed. A particle, a wave, a signal of any kind, all of them are bound by the cosmic speed limit. But the fabric of spacetime is not a thing moving through space. It is space, and it can stretch as fast as the equations say it stretches. In the early universe, during a period called cosmic inflation, space expanded so fast that regions of the universe were flung apart at speeds trillions of times faster than light. Not hypothetically, actually. The math demands it. The observations confirm it. Space does not care about speed limits because space is not going anywhere. It is just becoming more. The expansion is not a force. That is another thing people get wrong. Gravity is a force. Electromagnetism is a force. Expansion is not pushing galaxies apart the way an explosion throws debris. There is no shock wave, no outward pressure. The galaxies are not being shoved. They are simply finding that the space between them is increasing. If you could freeze a galaxy in place relative to the space immediately surrounding it, it would stay frozen. The expansion would continue around it, but the galaxy would not move. Expansion only affects objects that are not bound together by other forces. A galaxy is held together by gravity. The stars inside it are orbiting the galactic center. The gas clouds are being pulled inward. Gravity wins. Expansion loses. Same with galaxy clusters. Same with solar systems. Same with planets and moons and people. You are not expanding. The atoms in your body are held together by electromagnetic forces vastly stronger than the tug of cosmological expansion. You will never notice the universe getting bigger because the structures you are part of are immune to it. But step outside those structures, into the space between galaxy clusters, and there is nothing holding things together, no gravity strong enough to resist the expansion. Space stretches freely, and the farther apart two objects are, the more space there is between them, and the faster that space expands. This is why distant galaxies recede faster than nearby ones, not because they are moving faster through space, because there is more expanding space between us and them. The relationship is linear. Twice the distance, twice the recession speed, 10 times the distance, 10 times the speed. At some point, if the distance is large enough, the total rate of separation exceeds the speed of light. That threshold is called the Hubble radius. It sits at roughly 14 billion light-years. Anything farther than that is receding from us faster than light. We can still see those galaxies because the light they emitted in the past is still reaching us, but the galaxies themselves are now moving away faster than new light from them can ever catch up. They are slipping beyond the edge of what we will ever be able to observe. The expansion rate is not fast locally. If you measure how fast space is expanding right here in the Milky Way's neighborhood, the number is small. Roughly 70 kilometers per second per megaparsec. A megaparsec is about 3.26 million light-years. So for every 3.26 million light-years of distance you measure, space is expanding at an additional 70 kilometers per second. That does not sound like much. 70 kilometers per second is fast for a car. It is nothing for the cosmos. But scale it up. Go out 100 megaparsecs, 326 million light-years. Now the recession speed is 7,000 kilometers per second, 1,000 megaparsecs, 3.26 billion light-years, 70,000 kilometers per second. Keep going. At 10,000 megaparsecs, 32 billion light-years, the recession speed is 700,000 kilometers per second, more than twice the speed of light, and there is nothing out there moving, just space, stretching, doing what space does. Astronomers measure this using redshift. When a galaxy is moving away from us because space is expanding, the light it emits gets stretched, the wavelengths increase, colors shift toward the red end of the spectrum. The faster the galaxy is receding, the more the light is redshifted. You can measure the amount of redshift in a galaxy's spectrum and calculate how fast it is moving away. Do that for thousands of galaxies at different distances, and you can map the expansion rate of the universe. That is how Edwin Hubble discovered expansion in the first place back in 1929. He measured the redshifts of distant galaxies, plotted them against their distances, and found a clean relationship. Farther galaxies had higher redshifts. They were receding faster. Space was expanding. The universe was not static, it was growing. The stretching affects everything, not just galaxies. Light itself gets stretched as it travels through expanding space. A photon that leaves a distant galaxy as blue light might arrive at Earth as red light, or infrared, or even radio waves, depending on how much space has expanded during the photon's journey. The stretching does not slow the photon down. Light always moves at the speed of light, but the wavelength increases, the energy decreases. The photon is redshifted. This is why the most distant galaxies we observe look so red in images from the James Webb Space Telescope. They are not actually red. They are emitting ultraviolet and visible light. But space has stretched that light so much during its 13 billion-year journey that by the time it reaches us, it has been shifted deep into the infrared. We are seeing ancient blue light that has been pulled into the red by the expansion of the universe itself. The expansion is accelerating. That was the surprise discovery in 1998 that won 3 physicists the Nobel Prize. For most of the 20th century, cosmologists assumed the expansion was slowing down. Gravity, they thought, would gradually pull everything back together. The universe might eventually stop expanding and start contracting, the big crunch. Or maybe expansion would continue forever, but at an ever-decreasing rate, coasting to a stop over infinite time. Both options assumed gravity was the dominant force at cosmic scales. Turns out it is not. Something else is out there, something with negative pressure, something that pushes instead of pulls. Astronomers call it dark energy, and it is causing the expansion to speed up. Galaxies that were receding slowly are now receding faster. The Hubble constant is not constant, it is increasing, and the universe, instead of coasting or collapsing, is accelerating into a runaway expansion that will eventually rip everything apart. But dark energy is not the reason space can expand faster than light. That is a separate fact. Even in a universe with no dark energy, even in a universe where expansion was slowing down, space could still expand faster than light at large enough distances. The speed of expansion depends on the total amount of distance involved. More distance means more space. More space means faster total recession. You do not need acceleration for that. You just need scale. Dark energy makes the problem worse because it increases the rate of expansion everywhere over time. But the basic fact, that distant objects can recede faster than light because space itself is expanding was true long before dark energy was discovered. It has been true since the Big Bang. It will be true until the end of the universe. Space does not have a speed limit. Only the things moving through space do. If this sounds like a loophole, that is because it is. Special relativity says nothing can move through space-time faster than light. General relativity adds a footnote. Space-time itself is not bound by that rule. The fabric can stretch, contract, warp, or ripple. At any rate, the equations allow, and the equations allow space to expand as fast as it wants. The only limit is the energy density of the universe. The more matter and energy you pack into space, the more gravity you have, and gravity resists expansion. But in a universe dominated by dark energy, where the energy density has a repulsive component, expansion accelerates, and at large enough scales the recession speed exceeds light. Not because anything is moving, because the stage itself is getting bigger. This creates strange effects. There are galaxies we can see right now whose light is reaching us, but if we tried to send a signal back to them, the signal would never arrive. Even if we sent the signal at the speed of light, it would spend eternity trying to cross a gap that is widening faster than the signal can travel. The photon would never stop moving. It would never turn around. It would just never get there. Running full speed on a treadmill that is accelerating faster than it can run. The galaxy is visible to us because it sent its light billions of years ago when the distance was smaller and the expansion was slower. But the galaxy itself, as it exists right now, is beyond our reach. We are looking at a place we can never go, a destination that has already slipped beyond the horizon. The cosmic event horizon, the boundary beyond which we can never send or receive signals, sits at roughly 15 billion light-years from Earth. That is not the edge of the observable universe. We can see much farther than that because we are looking at light that was emitted long ago when those regions were closer. But anything happening right now beyond 15 billion light-years is invisible to us forever. And anything we do right now will be invisible to them forever. The expansion of space has severed the connection. We are causally disconnected, two regions of the same universe that can no longer affect one another in any way, and that boundary is shrinking. Every year, galaxies that were once inside the cosmic event horizon cross it and disappear from the list of places we could theoretically reach. The expansion is pulling them away faster than we can chase them. Even traveling at the speed of light, we could not catch up. Even if we left right now, we would fall farther and farther behind, watching the gap widen, the redshift increase, the galaxy fade into darkness as space stretched the distance faster than we could close it. The universe is not just large, it is tearing itself apart. And the tearing is accelerating. This is what space-time does. It is not a passive container, it is an active participant in the physics of the universe. It curves around massive objects, creating what we experience as gravity. It ripples when black holes collide, sending gravitational waves across billions of light-years. It stretches as the universe expands, carrying galaxies along with it like leaves on a river. And it does all of this without violating a single law of physics. The rules allow it. The math predicts it. The observations confirm it. Space is not required to sit still. It is not required to stay the same size. It is not required to respect the speed limit that applies to everything moving through it. Because space is not a thing, it is the arena, the canvas, the medium, and the medium is dynamic. The analogy that works best is the surface of a balloon. Imagine you draw dots on a deflated balloon with a marker. Each dot represents a galaxy. Now you start inflating the balloon. The dots do not move across the surface. They stay in the same spot on the rubber. but the distances between them increase. The surface is expanding, and if you measure how fast two dots are separating, the rate depends on how far apart they were to begin with. Dots close together separate slowly. Dots on opposite sides of the balloon separate much faster, not because they are moving faster, because there is more rubber between them and all of it is stretching at once. Now imagine the balloon has no inside and no outside. You cannot step off the surface. You cannot look at it from an external perspective. You live on the surface. It is the only space you have access to. The only directions you can move are along the surface. Forward, backward, left, right. There is no up or down in the sense of leaving the surface, and yet the surface is expanding. You can measure the expansion. You can see distant dots receding. You can calculate the rate. But if you ask what the surface is expanding into, the question does not make sense. There is no external space. The balloon is all there is. The expansion is happening within the surface itself. That is space-time. We live in it. We move through it. And it is stretching in a way that does not require an outside, because the stretching is a property of the geometry, not a motion into some larger container. The expansion is not uniform at small scales. Locally, space does not expand. The Milky Way is not getting bigger. The local group of galaxies, which includes the Milky Way, Andromeda, and a few dozen smaller galaxies, is not expanding. Gravity has bound these structures together tightly enough that the expansion of space has no effect. The galaxies are orbiting one another. Andromeda is actually moving toward us. It will collide with the Milky Way in about 4 billion years. The two galaxies will merge into a single larger galaxy. None of that would be possible if space were expanding everywhere uniformly. Gravity wins at small scales. It holds matter together, resists the stretching. Only at distances beyond the gravitational pull of galaxy clusters does expansion dominate. And those are the distances that matter when we talk about the universe as a whole. The big picture, the large-scale structure, the cosmic web of galaxies stretching across billions of light years, that is where space is expanding. That is where the stretching is visible. Physicists describe this with something called the Friedmann equations. They come from Einstein's general relativity, and they govern how the universe expands depending on what it contains: matter, radiation, dark energy. Plug in the contents of the universe, and the equations spit out an expansion rate. Change the contents, and the rate changes. In a universe dominated by matter, expansion slows over time. In a universe dominated by radiation, it slows even faster. In a universe dominated by dark energy, it accelerates. We live in the third kind. Dark energy makes up roughly 68% of the total energy density of the universe. Matter, both normal and dark, makes up the rest. And because dark energy dominates, the expansion is speeding up. The distances between galaxy clusters are growing faster and faster. The Hubble constant is increasing, and the universe is accelerating toward a state where almost nothing will be visible from anywhere because everything will have receded beyond the horizon. That future is billions of years away. For now, we can still see a large portion of the universe. We can map the distribution of galaxies. We can measure the expansion rate. We can trace the history of space-time back to the Big Bang and forward to the heat death. We can watch space stretch in real time by observing the redshifts of distant galaxies, and we can confirm that yes, space is expanding faster than light at large distances, not because anything is breaking the rules, because the rules were more subtle than anyone expected. Einstein gave us the framework in 1915, Hubble gave us the data in 1929, and decades of observations since then have confirmed what the equations predicted. Space is not fixed, it is not static, it is not a background, it is a participant, and it is stretching. This is the fabric of spacetime, not a metaphor, not a simplification, a real physical structure with measurable properties that bends, stretches, ripples, and evolves according to the laws of physics. It is the thing you are moving through right now, the thing holding you to the Earth, the thing separating you from the stars. And it is growing, expanding in all directions at once, carrying the galaxies with it, creating more distance, more space, more universe, without needing anywhere to expand into. Because space-time is not inside anything, it is the only thing. And what it does, the way it stretches, is driven by something we cannot see and do not fully understand. Something that makes up most of the universe and yet remains almost completely mysterious. Something with enough power to overpower gravity itself and tear the cosmos apart. The invisible engine that is accelerating the expansion, pushing space to stretch faster and faster, driving the universe toward an end we can predict but cannot prevent. The stretching of space is real, the measurements are solid, the observations are consistent, space is expanding, distances are growing, and galaxies are receding from one another faster the farther apart they are. For most of the 20th century, that was the story. The universe began in a hot, dense state and has been expanding ever since. Simple, elegant. Exactly what you would expect from an explosion that happened 13.8 billion years ago. The Big Bang throws everything outward, and then gravity gradually slows the expansion down. Over time, the rate of growth decreases. Eventually, maybe, the universe stops expanding altogether and starts collapsing back in on itself. The Big Crunch. Or maybe it expands forever but more and more slowly, coasting to a gentle stop over infinite time. Either way, gravity is doing what gravity does, pulling things together, resisting the expansion, slowing everything down. That was the model, gravity versus momentum, a cosmic tug-of-war between the outward push from the Big Bang and the inward pull of all the matter in the universe trying to collapse back together. The only question was which side would win. Then in 1998, two independent teams of astronomers measured the brightness of distant exploding stars and discovered that the universe was not slowing down. It was speeding up. That discovery did not just revise the model, it shattered it. Because if the expansion is accelerating, then something is pushing. Something with enough power to overpower gravity itself. Something that is not matter, not radiation, not anything on the periodic table. Something invisible, intangible, and utterly unprecedented. They called it dark energy, and it makes up 68% of the universe. The two teams were called the Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High Z Supernova Search Team, led by Brian Schmidt at the Australian National University and Adam Rees at Johns Hopkins. Both groups were doing the same thing, hunting for a specific type of exploding star called a Type 1, a supernova. These are useful because they are remarkably consistent. A Type 1, a supernova, happens when a white dwarf star, the dense leftover core of a sun-like star that has burned out, pulls material from a companion star until it reaches a critical mass, about 1.4 times the mass of the Sun. At that point, the white dwarf can no longer support itself. The core ignites in a runaway thermonuclear explosion that obliterates the entire star in a matter of seconds. The explosion is so powerful and so consistent that every Type 1, a supernova, produces roughly the same peak brightness. Astronomers call them standard candles, objects with a known luminosity that you can use to measure distance. If you know how bright something actually is, and you measure how bright it appears from Earth, you can calculate how far away it is. Simple geometry. The farther away it is, the dimmer it looks. By the mid-1990s, telescopes were powerful enough to detect Type 1, a supernovae in galaxies billions of light-years away. The plan was straightforward: find distant supernovae, measure their brightness, calculate how far away they are, then measure the redshift of the host galaxy to determine how fast it is receding. Plot distance against recession speed, and you get the expansion history of the universe. If expansion is slowing down, distant galaxies will be receding faster than you would expect based on their current distance, because the expansion was faster in the past. If expansion is constant, the relationship will be perfectly linear. Either way, the data will tell you how gravity has been affecting the expansion over billions of years. That was the theory. The data did something else. The supernovae were dimmer than they should have been, not by a little, by a lot. Enough that the only way to explain it was if the supernovae were farther away than their redshifts predicted. That should not have been possible. Redshift tells you how fast something is receding. Recession speed tells you the distance. The two should match. They did not. The supernovae were sitting about 15% farther away than the redshift said they should be. That meant the universe had expanded more than expected in the time since the light left those galaxies. More expansion means faster expansion. Faster expansion means something was accelerating it. Both teams checked their work. Both teams found the same result. The universe was not coasting. It was accelerating, speeding up, expanding faster now than it was in the past. And that made no sense. Gravity does not push, gravity pulls. Every particle of matter in the universe attracts every other particle. The more matter you have, the stronger the pull. And the universe has a lot of matter. Trillions of galaxies, each containing hundreds of billions of stars, plus gas, dust, black holes, planets, dark matter, all of it pulling on everything else. The combined gravity of all that mass should be slowing the expansion down, not dramatically. The universe is too spread out for gravity to reverse the expansion anytime soon, but it should be slowing. The rate of expansion should be decreasing over time. It was not. It was increasing. Something was overpowering gravity. Something with negative pressure. Something that pushes instead of pulls. And whatever it was, there was a lot of it. Michael Turner, a cosmologist at the University of Chicago, called it the greatest mystery in cosmology. He was not exaggerating. The discovery won Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011. Not because they found something expected, because they found something completely wrong. Something that should not exist according to any model anyone had built. And yet there it was in the data. Clear, consistent, undeniable. The universe is accelerating, and no one knows why. The simplest explanation, and the one most cosmologists currently favor, is something called the cosmological constant. It is not a new idea. Einstein invented it in 1917, a couple years after he published general relativity. At the time, Einstein believed the universe was static, eternal, and unchanging. But when he applied his equations to the universe as a whole, he found that they predicted an expanding or contracting cosmos. Space could not stay still. It had to grow or shrink. Einstein hated that. So he added a term to his equations specifically to counteract the pull of gravity and hold the universe in place. He called it the cosmological constant and labeled it with the Greek letter lambda. It represented a kind of energy built into the fabric of space itself, a vacuum energy, an intrinsic pressure that pushed outward just enough to balance gravity and keep the universe static. Then Hubble discovered that the universe was expanding, and Einstein removed the term. He reportedly called it his biggest blunder. The universe was not static, it was growing. The cosmological constant was unnecessary. Except it turns out it was not unnecessary, it was just misapplied. Because if you take Einstein's cosmological constant and set it to a small positive value instead of trying to balance gravity, you get exactly what the supernova data shows: an accelerating expansion. Space itself has energy, and that energy creates a kind of anti-gravity, a repulsive pressure that grows stronger as space expands, because more space means more vacuum energy. Gravity pulls matter together, vacuum energy pushes space apart, and because the universe is mostly empty space, vacuum energy wins. The idea is elegant. It explains the observations. It fits neatly into general relativity. It requires no new physics, just a single constant term in the equations. And it makes a clear prediction. The acceleration should be constant. Dark energy under this model is a property of space itself. It does not change over time. It does not dilute as space expands. Every cubic meter of empty space contains the same amount of vacuum energy, whether the universe is young or old, small or large. Matter dilutes as space grows because the same amount of stuff is spread over a larger volume. Radiation dilutes even faster because the wavelengths stretch, but vacuum energy does not dilute. It scales with volume. Double the volume of space and you double the total amount of dark energy. That is why dark energy dominates now but did not in the early universe. In the beginning, the universe was dense. Matter and radiation were packed together tightly. Gravity was strong, expansion was slowing, but as space grew, matter spread out. Gravity weakened, and vacuum energy, which does not dilute, eventually became the dominant force. Current estimates put the transition at about 5 billion years ago. Before that, gravity was winning. The expansion was slowing. After that, dark energy took over. The expansion started speeding up, and it has been accelerating ever since. If the cosmological constant is correct, the universe will expand forever, faster and faster, with no limit, until every galaxy outside our local group has receded beyond the cosmic horizon. The night sky will go dark, stars will burn out, black holes will evaporate, and eventually, trillions of years from now, the universe will be a cold, empty, isolated void where nothing can ever interact with anything else again because the distances will have grown too large. Cosmologists call it the Big Freeze, or sometimes heat death. The slow, quiet ending where the universe does not collapse or explode, it just fades. Every structure that ever existed dissolving into darkness as space stretches into infinity. That is one possibility. The other is that dark energy is not a constant, that it is something dynamic, a field that changes over time. Physicists call this idea quintessence, after the classical fifth element that was supposed to fill the heavens. Quintessence models propose that dark energy is not vacuum energy but a new kind of field, similar to the fields that generate the forces we already know. The electromagnetic field, the Higgs field. A quintessence field would permeate all of space, just like vacuum energy, but its strength could vary. It could increase over time, driving the expansion faster and faster until space itself tears apart in a big rip. Or it could decrease, allowing gravity to eventually slow the expansion and maybe even reverse it, leading to a big crunch. Or it could oscillate, cycling between expansion and contraction in an eternal cosmic rhythm. Quintessence is more complicated than the cosmological constant. It requires new physics, new fields, new particles. But it has one major advantage. It could explain why dark energy is so weak. This is called the cosmological constant problem, and it is one of the biggest unsolved puzzles in physics. If dark energy is vacuum energy, then quantum field theory, the branch of physics that describes particles and forces, predicts how strong it should be. The prediction is insane. The equations say vacuum energy should be about 10 to the power of 120 times stronger than what we actually observe. That is 1 followed by 120 zeros, the largest mismatch between theory and observation in the history of science. If vacuum energy were actually that strong, the universe would have blown itself apart a fraction of a second after the Big Bang. Galaxies would never have formed. Stars would never have ignited. We would not exist. The fact that we do exist means something is cancelling out almost all of that vacuum energy. Some mechanism, some symmetry, some principle we do not understand is driving the value down to an incredibly small but non-zero number, and no one knows what that mechanism is. Quintessence avoids this problem by making dark energy a separate field with its own dynamics. The field starts with a certain value and evolves over time according to its own rules. You can tune the rules to produce the observed acceleration without invoking vacuum energy at all. The downside is that quintessence is harder to test. The cosmological constant makes a single clear prediction. The acceleration is constant. Quintessence makes many possible predictions depending on how you set up the field. Some versions predict the acceleration will increase. Some predict it will decrease. Some predict it will stay roughly the same for billions of years and then suddenly change. You need extremely precise measurements of the expansion rate at different points in cosmic history to distinguish between the models, and even then, the differences might be too small to detect. Current data slightly favors the cosmological constant. Observations of the cosmic microwave background radiation from the Planck satellite, measurements of distant supernovae, surveys of galaxy clustering, all of it fits a universe where dark energy is constant to within a few percent. But the error bars are still large enough that quintessence is not ruled out. And some recent measurements have hinted at small deviations that could point to a dynamic dark energy. The jury is still out. What is not in doubt is that dark energy exists, the acceleration is real, the universe is speeding up. And whatever is causing it, dark energy makes up roughly 68% of the total mass energy content of the universe. Dark matter, the invisible stuff that holds galaxies together, makes up another 27%. Ordinary matter, atoms, everything you have ever seen or touched, everything on Earth, every star, every planet, every gas cloud, adds up to about 5%. We are the minority. The vast majority of the universe is stuff we cannot see and do not understand. Dark energy does not interact with matter. It does not clump. It does not emit light. It does not absorb light. It does not generate magnetic fields or electric charges. It just sits there, filling space, exerting pressure. You cannot shield yourself from it. You cannot detect it directly. The only reason we know it exists is because we can see its effect on the large-scale structure of the universe. Galaxies are moving apart faster than they should. Space is expanding faster than gravity can resist. That is the evidence. That is all the evidence. No particle detector has ever found a dark energy particle. No telescope has ever seen dark energy directly. We infer its existence the same way you infer the existence of wind by watching trees bend. You cannot see the wind. You see what it does. Dark energy is not a force in the traditional sense. It does not pull or push on individual objects the way gravity or electromagnetism does. It affects space-time itself. It changes the geometry. When you add dark energy to the equations of general relativity, the curvature of space-time shifts in a way that makes distances grow faster over time. The effect is negligible at small scales. Dark energy has no measurable impact on the solar system. It does not change the orbit of planets. It does not affect the motion of stars within galaxies. Gravity dominates at those scales. Dark energy only matters when you step back and look at the universe as a whole, at distances of hundreds of millions of light years and larger. That is where the acceleration shows up. That is where space is stretching fast enough that dark energy overpowers gravity. There are alternative explanations. Some physicists have proposed that instead of dark energy, the acceleration could be caused by a modification to general relativity itself. Maybe gravity does not work the way Einstein described it at very large scales. Maybe there is an additional term in the equations that only becomes important when you are dealing with distances comparable to the size of the observable universe. These modified gravity theories can reproduce the observed acceleration without invoking dark energy at all. The problem is that they struggle to match all the other data: the cosmic microwave background, galaxy clustering, the large-scale structure of the universe. General relativity with a cosmological constant fits everything. Modified gravity fits some things but breaks others. Most cosmologists do not take these ideas seriously, not because they are impossible, because they are less successful at explaining the full range of observations. Dark energy is here to stay until something better comes along, and so far, nothing better has come along. The discovery in 1998 was 26 years ago. In that time, thousands of additional supernovae have been measured. Multiple independent surveys have mapped the expansion history in exquisite detail. Satellites have measured the cosmic microwave background to a precision of a few parts per million. The European Space Agency launched a mission called Euclid specifically to study dark energy. NASA is planning a mission called the Nancy Grace Roman Space Telescope that will measure the distances to millions of galaxies to constrain the properties of dark energy even further. Every new observation has confirmed the same thing. The universe is accelerating, dark energy is real, and we have no idea what it is. Michael Turner was right to call it the greatest mystery in cosmology, but it is more than that. It is a signal that something is fundamentally missing in our understanding of the universe. The standard model of particle physics, the theory that describes all known particles and forces, does not predict dark energy. It does not even have room for it. Quantum field theory, the framework that underlies the standard model, predicts vacuum energy but gets the value wrong by 120 orders of magnitude. General relativity allows for a cosmological constant, but does not explain why it has the value it does or where it comes from. The two pillars of modern physics, quantum mechanics and relativity, both fail to account for the dominant component of the universe. That is not a small gap. That is a chasm. Some physicists think the solution will come from a theory of quantum gravity, a unified framework that merges quantum mechanics and general relativity into a single consistent description of nature. String theory is one candidate. Loop quantum gravity is another. Both predict new phenomena at extremely high energies that could in principle explain dark energy. But neither has been tested, and both require math so abstract that most physicists cannot follow it without years of training. The ideas are beautiful, the predictions are untestable, and the connection to dark energy is speculative at best. The uncomfortable truth is that we are flying blind. We have measured the effect, we can describe the behavior, we can predict the future evolution of the universe based on the current data, but we do not know what we are looking at. Dark energy could be vacuum energy, it could be a new field, it could be a sign that general relativity breaks down at cosmic scales. It could be something else entirely, something we have not thought of yet. And until we figure it out, the majority of the universe remains a mystery. Not the fun kind of mystery where you have a few clues and you are narrowing down the suspects. The kind of mystery where you do not even know what questions to ask. This is the invisible engine driving the expansion of the universe. A force or a field or a property of space itself that has been accelerating the cosmos for the last 5 billion years and shows no sign of stopping. It is not dark matter. Dark matter pulls things together. Dark energy pushes them apart. It is not ordinary energy. Ordinary energy dilutes as space expands. Dark energy does not. It is not a mistake in the data. The measurements have been checked and rechecked by independent teams using different methods. It is not a failure of instruments. Supernovae are among the most reliable distance indicators in astronomy. The acceleration is real, the universe is speeding up, and the thing causing it is invisible, intangible, and utterly dominant. If you could somehow remove all the dark energy from the universe, the acceleration would stop immediately. Expansion would continue, but it would start slowing down. Gravity would take over. Galaxies would stop receding so quickly. The cosmic event horizon would stop shrinking. The universe would settle into a long, slow, coasting expansion that might eventually reverse into a collapse. Or it might continue forever at an ever-decreasing rate, asymptotically approaching zero but never quite stopping. Either way, the future would be different. The fact that dark energy exists changes everything. It changes the fate of the universe. It changes the ultimate destiny of every galaxy, every star, every planet. It changes how long structures can survive before the expansion tears them apart. And it changes the timeline for when the night sky will go dark. That future is not imminent. The acceleration is slow, measured in kilometers per second per megaparsec, at human scales, at planetary scales, even at galactic scales. You will never notice it. But over billions of years, the effect is catastrophic. Galaxies outside our local cluster are already receding faster than light. In a few 100 billion years, every galaxy beyond the local group will have crossed the cosmic horizon. Their light will no longer reach us. New stars will form for a while, but eventually the gas will run out. Stars will die, and no new ones will replace them. The galaxies will dim, then go dark. Black holes will persist for trillions of years, but eventually even they will evaporate through Hawking radiation. And then there will be nothing, just space. Expanding, accelerating, empty, forever. That is what dark energy does. It does not destroy the universe in a sudden cataclysm. It pulls it apart slowly, methodically, inevitably, and there is no way to stop it. You cannot turn off dark energy. You cannot shield yourself from it. You cannot escape it by moving to a different part of the universe, because every part of the universe is accelerating. The only places that survive are the regions where gravity is strong enough to hold structures together. Galaxy clusters, galaxies, solar systems, planets, for now. But even those islands of stability are temporary. Eventually, as dark energy continues to dominate, even bound structures might begin to feel the strain. Some models predict that if dark energy increases over time, it could eventually grow strong enough to overcome gravity at smaller and smaller scales, tearing apart galaxy clusters, then galaxies, then solar systems, then planets, then molecules, then atoms, the Big Rip. A scenario where the universe does not fade quietly but is shredded by runaway acceleration that pulls everything apart down to the subatomic level. Most physicists think the Big Rip is unlikely. The data suggest dark energy is constant, but the possibility exists, and the fact that we cannot rule it out tells you how little we understand about what dark energy actually is. 68% of the universe is made of something we cannot see, cannot touch, cannot explain, and can barely describe. It does not show up in particle accelerators. It does not appear in telescopes. It does not interact with matter or light. It just sits there, filling space, pushing the universe apart, and defying every attempt to understand it. And it is not going away. It is getting stronger. Not because dark energy itself is increasing, but because space is expanding and more space means more dark energy. The universe is feeding the thing that is tearing it apart. The more it grows, the faster it grows, and there is no mechanism to stop it. This is the engine, the invisible force that has hijacked the expansion and turned it into a runaway acceleration. Gravity had its chance. For the first 9 billion years, gravity was slowing the expansion. Then dark energy took over, and once it did, there was no going back. The universe crossed a threshold. Acceleration replaced deceleration, and now the cosmos is accelerating toward an end we can predict but cannot prevent. The big freeze, the heat death, the era when every galaxy is alone, every star is dark, and space itself is all that remains. Stretching, expanding, accelerating, into a future so distant and so empty that it is almost impossible to imagine. But that future is written into the equations, it is built into the data, it is the inevitable consequence of living in a universe dominated by dark energy, a force we do not understand, a property of space we cannot explain, an engine we cannot turn off. And the realization that the thing shaping the fate of everything is something we know almost nothing about is, in its own way, more unsettling than any edge or boundary could ever be, because at least an edge is something you can point to. Dark energy is everywhere, and nowhere, and it is winning. 68% of the universe is something we cannot see. 27% is dark matter holding galaxies together through gravity we can measure, but matter we cannot find. 5% is everything else, atoms, stars, planets, you, and all of it 100% is expanding, accelerating, stretching into a future where distances grow so large that light itself cannot cross them. That is the story so far. Space is not static. It is dynamic. It bends, ripples, stretches, and the stretching is driven by an invisible engine called dark energy that overpowers gravity and tears the cosmos apart. But all of that, every measurement, every equation, every observation, leads to the question that will not go away. The question that sits at the back of every conversation about cosmology like an uninvited guest. If the universe is expanding, what is it expanding into? You have heard the answer. Space is not expanding into anything. The universe is not growing inside a larger container. There is no outside. There is no room that the cosmos is filling. Space itself is what is getting bigger. The distances between objects are increasing because new space is being created. That is the answer. And if you are like most people, that answer does not satisfy you, because your brain, wired by millions of years of evolution to navigate a world of boundaries and containers and edges, keeps insisting that if something is getting bigger, it must be getting bigger inside something else. A balloon expands into the room. A city expands into the countryside. A drop of ink expands into water. Everything that grows does so by occupying space that was already there. That is how growth works, except when it does not. The universe is not a thing inside space. It is space. And the question, what is the universe expanding into, is not a question about missing information. It is a question built on a broken assumption, the assumption that space is a container, that the universe exists inside something, that there is an exterior, an outside, a surrounding medium. There is not, and the reason there is not goes deeper than most people realize. It is not that we have not found the outside yet, it is that the concept of outside does not apply. Asking what the universe is expanding into is like asking what is north of the North Pole. The question sounds reasonable. It uses words you understand, arranged in a grammatically correct order. And yet the question has no answer, not because we do not know the answer, because the question itself does not make sense, Stand at the North Pole. You are at the northernmost point on Earth. Every direction you can walk is south. There is no north from there. You cannot go more north. North has run out. The concept has reached its limit. Now someone asks you, what is north of the North Pole? You could say nothing. You could say the question is meaningless. You could explain that north is a direction defined by the geometry of Earth's surface, and once you reach the pole, the direction ceases to exist. All of those answers are correct, but none of them feel satisfying because the question sounds like it should have an answer. It has the structure of a question that makes sense. What is north of New York? Canada. What is north of Canada? The Arctic. What is north of the Arctic? The North Pole. What is north of the North Pole? The question breaks, not because you have reached a wall or a barrier, because you have reached the edge of what the question can describe. North is a direction on a curved surface. The North Pole is the point where that direction converges. Beyond that point, the concept does not extend. There is no more north. Not because something is blocking it, because north is over. The universe works the same way. Space is not a stage. It is not a container holding galaxies the way a jar holds marbles. Space is a relational concept, a way of describing the distances and orientations between objects. When we say two galaxies are 1,000,000 light-years apart, we are describing the geometry of space-time between them. We are not saying they are embedded in some pre-existing grid. The grid is generated by the presence of the objects and the structure of space-time itself. Remove the objects, remove the space-time, and there is no grid, no distance, no separation, no space. Space is not a thing you can have without a universe. It is a property of the universe. And asking what is outside the universe is like asking what is outside space. The question assumes space is inside something. It is not. Space is the thing that makes inside and outside possible in the first place. You cannot step outside it, because outside is a concept that only exists within space. Here is another way to think about it. Imagine you are a character in a video game. You live in a two-dimensional world. You can move left, right, up, down. Those are the only directions you have. The world you inhabit is a flat plane. You walk to the edge of the map and you hit a boundary. Beyond the boundary, the game has not rendered anything. There are no pixels, no terrain, no objects. You ask, what is beyond the edge? And the answer is nothing. Not nothing as in empty space. Nothing as in the concept of space does not extend beyond the boundary. The game world is all there is. Outside the game, there is a computer running the code. There is a room where the computer sits. There is a person playing the game, but none of those things exist inside the game world. From your perspective as a character in the game, the universe is the map. The map is not inside anything. It is the only thing. You can ask what is beyond it, but the question does not have an answer that makes sense within the rules of your world. Because beyond is not a place you can go. It is not a direction you can point. It is a concept that does not apply. We are in the same position. We live inside space-time. 3 dimensions of space, 1 dimension of time, woven together into a 4-dimensional structure that defines every possible location and moment. Space-time is the map, and as far as we can tell, it is not embedded in anything. It is not sitting inside a 5-dimensional container. There is no exterior medium, no surrounding void. The universe is space-time. Space-time is the universe. And asking what is outside space-time is asking for a direction that does not exist. Not because something is blocking the way, because the direction is not part of the geometry. It is not on the map. Einstein's general relativity describes space-time as a manifold. That is the technical term. A manifold is a mathematical structure that is self-contained. It does not need to be embedded in anything larger to exist. The surface of a sphere is a two-dimensional manifold. You can walk anywhere on the surface. You can measure distances. You can describe locations. You can map the entire thing without ever leaving the surface. And you do not need a three-dimensional space for the sphere to exist in. The surface itself is all you need. Mathematically, you can define the surface, describe its curvature, calculate distances along it, all without reference to any exterior space. The sphere is not inside anything. It is a complete self-contained structure. Spacetime works the same way. It is a four-dimensional manifold. It has its own geometry, its own curvature, its own rules, and it does not require a five-dimensional space to exist in. The equations of general relativity describe how spacetime curves in response to mass and energy. They describe how objects move through spacetime. They describe how distances change as the universe expands. And none of that requires an exterior. The manifold is complete on its own. The universe is not inside anything because inside is a concept that only makes sense within the universe. You cannot step outside spacetime any more than you can step outside of existence, because outside and existence are both concepts defined by spacetime. Remove spacetime and the concepts stop meaning anything. This is not a cop-out. It is not scientists refusing to answer the question because they do not know. It is scientists telling you that the question is built on a misunderstanding. The misunderstanding is that space is a thing that can have an outside. It is not. Space is the framework that defines what outside means. You cannot apply the concept to the framework itself. It is like asking what time it was before time existed. The question uses the word before, which is a temporal concept. But if time does not exist, then before does not exist either. The question collapses under its own assumptions. Same with asking what is outside the universe. The question uses the word outside, which is a spatial concept. But if space is the universe, then outside does not exist. The question is trying to use a concept that only makes sense inside the thing it is asking about. It is circular, and it cannot be answered because it is not actually asking anything coherent. The reason this feels unsatisfying is because our intuition is wired for a different kind of reality. Every object you have ever encountered exists inside something else. You are inside a room. The room is inside a building. The building is inside a city. The city is inside a region. The region is inside a country. The country is on a planet. The planet is in a solar system. The solar system is in a galaxy. The galaxy is in a cluster. The cluster is in a supercluster. The supercluster is in the observable universe. And your brain, following the pattern, assumes the universe must be inside something too. Another structure, another layer, another container, because that is how everything else works. Except it is not how everything works. It is how things work inside the universe. The universe itself is the exception. It is the base layer, the foundation, the thing that contains everything else but is not contained by anything. And the reason we know that is because the math says so. General relativity does not require an exterior. The equations are complete without one. Adding an exterior does not make the equations work better. It makes them more complicated for no benefit. Occam's razor says the simplest explanation that fits the data is usually correct. The simplest explanation is that the universe is self-contained. No outside, no container, no embedding in a higher dimensional space, just spacetime doing what spacetime does. Some people find this idea comforting. The universe is everything. There is nothing beyond it to worry about. No larger structure threatening to collapse. No external forces interfering. The cosmos is complete, self-sufficient, eternal in its own way. Others find it deeply unsettling, because if there is no outside, then there is no escape, no place to go if something goes wrong. No refuge beyond the observable universe. You are stuck inside the thing, and the thing, as we have established, is tearing itself apart. Dark energy is accelerating the expansion. Galaxies are receding. The cosmic horizon is shrinking, and there is nowhere to run, because there is no outside to run to. You are trapped inside a universe that is expanding into itself, and the expansion is permanent. But trapped is the wrong word, because trapped implies there is somewhere else you could be. There is not. The universe is not a prison. It is reality, the totality of everything that exists, and everything that exists is, by definition, inside the universe. There is no outside, because outside would have to be something, a place, a region, a volume, and if it were something, it would be part of the universe. The universe is not a subset of a larger whole. It is the whole. Asking what is beyond it is like asking what is beyond existence. The question assumes existence is a limited category. It is not. Existence is everything by definition. If something exists, it is part of the universe. If it does not exist, then it is not outside the universe. It is just not. Nothing is not a place. It is the absence of place. And you cannot expand into an absence. You cannot move into nothing, because nothing is not a destination. It is the lack of one. This is where language starts to fail. The words we use to describe the universe are borrowed from our experience of objects inside the universe. We talk about the universe expanding, and our brains picture a balloon inflating into a room. We talk about the edge of the observable universe, and we picture a wall, a boundary, a place where things stop. But space is not a balloon, and the edge of the observable universe is not a wall. It is a horizon, a limit on how far we can see, not a limit on what exists. The universe does not stop at the edge of our vision. It keeps going. How far, we do not know. Maybe it goes on forever. Maybe it loops back on itself. Maybe it has some exotic topology we cannot visualize. But whatever it does not do it inside something else, because there is no something else, there is only the universe. The analogy that works best is the surface of a balloon again. But this time, imagine you are a two-dimensional creature living on the surface. You cannot look up or down. Those directions do not exist for you. You can only move along the surface, forward, backward, left, right. The surface is your entire universe. Now someone inflates the balloon. The surface expands. Every point on the surface gets farther from every other point. You can measure the expansion. You can see distant points receding. You ask, what is the surface expanding into? And the answer, from your perspective as a creature confined to the surface, is nothing. The expansion is happening within the geometry of the surface itself. The third dimension, the one the balloon is inflating into, does not exist in your reality. You cannot access it. You cannot point to it. You cannot describe it using the two dimensions you have. It is not part of your universe. The expansion does not require it. The surface can expand perfectly well according to its own internal rules without invoking an external space. The geometry changes, the distances increase, and that is all there is. We are in the same situation. We live in 3 dimensions of space. The universe is expanding, distances are increasing, and we ask, what is it expanding into? The answer is nothing. Or more precisely, the expansion is happening within the geometry of space-time itself. If there is a 4th spatial dimension, a direction we cannot access or perceive, then maybe space-time is embedded in that, but we have no evidence for it, no measurement requires it, and invoking it does not help explain anything. The equations work without it, the observations fit without it. Adding an extra dimension is unnecessary. So the simplest answer, the one that fits the data, is that spacetime is not embedded in anything. It is a self-contained manifold. The expansion is a change in the internal geometry, not a motion into an external space. This raises a different question. If the universe is everything, then what was there before the Big Bang? If time itself began at the Big Bang, then before does not make sense. There is no time before time, no moment prior to the first moment. The question is using a temporal concept, before, to ask about a state where time does not exist. Same problem as asking what is outside space. The question assumes the concept applies. It does not. Time is a dimension of space-time. Space-time began at the Big Bang. There is no before, because before is a direction in time, and time did not exist yet. The universe did not come into existence inside a pre-existing void. It came into existence along with the void. Space and time and matter and energy all erupted into being at the same instant. There was no stage waiting for the performance. The stage and the performance started together. Some physicists have proposed models where time is cyclic, where the universe expands, contracts, crunches back down to a singularity, and then bounces, starting a new Big Bang. In those models, there is a before, but it is part of a previous cycle, not an external timeline, just an earlier phase of the same universe. Other models suggest time is emergent, that at the quantum level, time does not exist in the way we experience it, that what we call time is a large-scale statistical phenomenon that breaks down near the Big Bang. In those models, asking what happened before the Big Bang is like asking what happened before cause and effect existed. The question assumes causality, but if causality is emergent, then the question does not apply at the Planck scale. The universe did not have a cause. It just is, or was, or will be. The tenses stop making sense because tense is a feature of time, and time is a feature of the universe, and the universe is not inside anything where external time could be ticking. This is the unthinkable outside, not a place, not a void, not a container, the absence of all those things. The recognition that the universe is not in anything because in is a concept that only makes sense within the universe. You cannot step outside reality. You cannot ask what reality is inside, because reality is the boundary, it is the limit, it is the thing beyond which concepts stop applying. And every attempt to visualize it, to picture it, to imagine what it looks like from the outside is doomed to fail. Because visualization requires space. Space requires the universe, and the universe is what you are trying to step outside of. It is circular, it is self-referential, and it is, in its own way, the most honest answer physics has ever given. We do not know what is outside the universe because the question does not make sense, and not knowing is not a failure, it is a boundary. A place where the map ends not because we have not explored far enough, but because the territory itself ends. The universe is not inside anything, it is the only thing. And that is as far as the question can go. The philosophical implications are staggering. If there is no outside, then there is no objective reference frame, no external observer watching the universe unfold. No higher perspective from which the cosmos can be viewed. Everything that exists is inside the thing. Every measurement is made from within. Every observation is local. There is no view from nowhere, no God's eye view, no absolute frame. Just observers inside spacetime, trying to make sense of the structure they are embedded in. And that structure, spacetime, is all there is. It is not sitting on a foundation. It is not floating in a void. It is not contained by anything. It is the foundation, the void, the container, and the thing contained, all at once. This is what cosmology has been trying to tell us for a century. The universe is stranger than we thought, bigger than we imagined, older than we expected, and fundamentally different from the kind of space we navigate every day. It does not have an outside because outside is a concept that only makes sense for objects within the universe. The universe is not an object, it is the totality, the everything, and everything by definition does not have an exterior. You cannot draw a circle around existence, because the act of drawing a circle requires space, and space is part of existence. The boundary is not out there somewhere waiting to be found. The boundary is the concept itself. Asking what is outside the universe is asking what is outside. It is asking for a direction beyond all directions, a place beyond all places. And the answer is not that we have not found it yet. The answer is that it does not exist, not as a location, not as a void, not as anything. The universe is not expanding into something, it is expanding into itself, creating more space as it goes, and that space is not being added from an external reservoir. It is being generated by the dynamics of spacetime itself. This is the edge of human understanding, not the edge of the observable universe, the edge of what we can conceptualize, the limit of language, the boundary where questions stop having answers, not because the answers are hidden, but because the questions are malformed. We are pattern recognition machines, evolved to navigate a world of objects and boundaries and containers, and we are trying to apply those patterns to a structure that does not fit them. The universe is not a container. It does not have an inside and an outside. It is a manifold, a self-contained geometric structure that defines its own distances, its own curvature, its own rules, and it does all of that without needing to be embedded in anything larger. The math works, the observations fit, and the conclusion, uncomfortable as it is that the universe is complete. There is no outside, no beyond, no next level up. Just space-time stretching, expanding, evolving according to the equations of general relativity. And those equations do not require an exterior. They never did. So when you ask what the universe is expanding into, the answer is not a place. It is a recognition. The recognition that the question is built on an assumption that does not hold. Space is not a thing that can have an outside. It is the thing that makes outside possible. And the universe, being made of space, cannot be inside anything because inside is a concept that only exists within the universe. This is not a dodge. It is not an evasion. It is the most honest answer physics can give. The universe is everything, and everything does not have an outside. It has an edge, yes, the edge of the observable universe, the cosmic horizon beyond which light has not had time to reach us. But that edge is not a wall. It is a limit on information, a boundary in time, not space. Beyond it, the universe continues. How far, we do not know. But wherever it goes, it does not go into something else. It just goes, expanding, stretching, creating more of itself as it grows. And that process, strange as it sounds, is all there is. No container, no outside, no unthinkable void waiting beyond the edge. Just the universe, alone, complete, eternal in its own self-contained way. And if that feels like an incomplete answer, it is only because the question was asking for something that does not exist. The outside is not out there, it never was. And the sooner we accept that, the sooner we can start asking better questions. Questions about what the universe is, not what it is inside, because what it is inside is nothing, and nothing is not a place, it is the absence of place, and you cannot expand into an absence. You can only expand, and that is exactly what the universe is doing right now, everywhere, into itself. The universe is leaving us behind, not metaphorically, not as a poetic way of describing cosmic indifference. Literally, right now, at this exact moment, galaxies are crossing a boundary in space beyond which we will never see them again. Not because they are dying, not because they are too faint, because the expansion of space is carrying them away so fast that their light will never reach us, not in a billion years, not in a trillion, never. They are slipping beyond a horizon from which there is no return. And once they cross it, they are gone, permanently, irretrievably, lost to us forever. That boundary has a name. Astronomers call it the cosmic event horizon, and it sits at roughly 16 billion light-years from Earth. That is not the edge of the observable universe. We can see much farther than that. The observable universe extends out to 46.5 billion light-years. We can see galaxies sitting near that edge right now because the light they emitted billions of years ago is still arriving. But the galaxies themselves, as they exist today, are receding from us faster than the speed of light. Space is expanding so rapidly between us and them that no new light they emit will ever complete the journey. We are seeing their past, but their present and their future are already unreachable. They have crossed the horizon, and they are not coming back. The cosmic event horizon is different from the edge of the observable universe. The observable universe is defined by how far light has had time to travel since the Big Bang. It is a sphere around us, centered on Earth, that grows slowly as the universe ages. Every year, light from slightly more distant regions reaches us for the first time. The observable universe expands, slowly, at roughly 1 light-year per year. But the cosmic event horizon is not expanding, it is shrinking, because the expansion of space is accelerating. Dark energy is pushing galaxies apart faster and faster, and the faster they recede, the harder it becomes for light to cross the gap. The event horizon marks the point where recession speed equals the speed of light. Beyond that distance, galaxies are moving away faster than light can travel toward us, and anything beyond that point is lost. Think of it this way. You are standing on a moving walkway at an airport, the kind that pulls you forward while you walk. You start walking toward the far end. The walkway is moving in the same direction you are walking, so you make progress. You are moving forward relative to the floor. Now imagine the walkway starts speeding up. You keep walking at the same pace, but the walkway accelerates. At some point, the walkway is moving so fast that even though you are still walking forward, you are not making any progress toward the end. You are being carried backward faster than you can walk forward. You will never reach the far end, not because you stopped moving, because the floor is moving faster than you can walk. That is what is happening to light from distant galaxies. The light is moving toward us at the speed of light, but space is expanding so fast that the light is being carried backward. It will never arrive. The photon keeps moving. It never stops, it never slows down, but the destination recedes faster than the photon can approach it, and the gap just keeps growing. This is not a new problem. Light from the most distant galaxies has been fighting this battle since it left. Every photon that reaches us from the edge of the observable universe spent billions of years struggling to cross a gap that was widening the entire time. Most of those photons lost the fight. They are still out there, still traveling, still aimed at Earth, but they will never get here. The ones that did make it left their galaxies when the universe was younger and the expansion was slower. Back then, the gap was small enough that light could make progress. It could cover more distance per year than space was adding. Slowly, over billions of years, those photons crossed the divide. But the galaxies they left are no longer where they were. Space has stretched, the galaxies have been carried away, and new light leaving those galaxies today is fighting a losing battle. The expansion is too fast. The gap is too wide. The horizon has moved. The event horizon sits at about 16 billion light-years right now. That is the comoving distance. The actual physical separation between us and a galaxy sitting at the event horizon, accounting for all the expansion that has occurred. If you could freeze the universe right now and measure the distance with a very long ruler, that is what you would get. 16 billion light-years. Anything farther than that is receding faster than the speed of light. And here is the uncomfortable part. We can see galaxies that are already beyond the event horizon. A lot of them, because the light we are seeing left those galaxies billions of years ago when they were closer and the expansion was slower. We are looking at their past. The past is still arriving, but their present is already gone. If a supernova exploded right now in a galaxy 17 billion light-years away, we would never see it. The light would leave the supernova, travel toward us at 300,000 kilometers per second, and spend eternity trying to close a gap that is growing faster than it can travel. The photon would never stop moving. It would never turn around. It would just never arrive. Running at full speed on a treadmill that is accelerating. This is the horizon, not a wall, not a boundary in space, a limit in causality, a line beyond which information cannot reach us, ever, no matter how long we wait. The galaxies beyond that line are still there. They are still shining. They are still full of stars and gas and dust, and perhaps even civilizations looking up at their own skies and wondering the same things we are. But they are invisible to us, not because they are too faint, because the light cannot get here. Space is expanding too fast. The distance is growing too quickly, and the separation is absolute, and it is getting worse. The cosmic event horizon is not fixed. It is shrinking. Right now, it sits at about 16 billion light-years, but as dark energy continues to accelerate the expansion, the horizon moves closer. Galaxies that are currently just inside the event horizon will cross it in the future. Galaxies we can see today will fade from view, not because they are dying, because they are being carried away. The light they are emitting right now will never reach us. The last photons that will ever arrive from those galaxies are already on their way. Once those photons get here, that is it. No more light will follow. The galaxy will dim, redshift into darkness, and disappear forever. We will have watched the last moment we will ever see from that part of the universe. Current estimates suggest the event horizon will eventually shrink to about 3 billion light-years. That is where it will stabilize if dark energy remains constant. Everything beyond that distance will cross the horizon and vanish. Right now, we can observe roughly 2 trillion galaxies within the observable universe. In the far future, billions of years from now, observers on Earth or wherever Earth used to be will look out into space and see almost nothing. A few dozen galaxies in the local group, Andromeda, the Milky Way, which will have merged with Andromeda by then into a single larger galaxy, a handful of smaller satellite galaxies, and that is it. The rest of the universe will have receded beyond the horizon. The night sky will go dark. Not because the stars burned out, because space stretched too fast. The galaxies will still be there, billions of them, trillions of them, still shining, still forming stars, still hosting planets and moons and perhaps even life, but they will be invisible, completely and permanently cut off from us, not by distance alone, by the structure of space-time itself. The expansion will have severed the connection. We will never see them. They will never see us. 2 regions of the same universe that can no longer communicate. No signals, no light. No information of any kind will ever cross the gap. The universe will have split into causally disconnected regions, islands of space that can never touch. This has already happened to most of the universe. The vast majority of galaxies that exist right now are already beyond our event horizon. We will never see them, not because they are too far away in the traditional sense, because light from them has not had time to reach us yet and never will. The event horizon is closer than the edge of the observable universe, much closer. We can see out to 46 billion light-years, but we can only interact with objects within 16 billion light-years. Everything beyond that is visible only as a ghost, a memory, an image from the past that no longer corresponds to anything we could ever reach or affect. We are looking at places that, from our perspective, have already ceased to exist as part of our causal universe, and the process is irreversible. Once a galaxy crosses the event horizon, it is gone. There is no way to pull it back, no way to slow the expansion, no way to prevent the separation. Dark energy does not turn off. Space does not stop stretching. The acceleration is built into the fabric of the cosmos. It is not a temporary phase, it is the future, and the future is one where the universe becomes lonelier and lonelier as more and more of it slips beyond reach. Every year, galaxies cross the horizon. Every year, the observable universe grows slightly as new light arrives from farther regions. But every year, the reachable universe shrinks as more galaxies recede beyond the point of no return. We can see more, but we can touch less. The view is expanding. The cage is closing. There is something deeply unsettling about this, not just scientifically, but existentially. The idea that most of the universe is already lost to us. That we are living in a brief window of time where we can still observe a significant portion of the cosmos. That future civilizations, if they exist, will look up at a nearly empty sky and have no way of knowing that billions of galaxies once filled the view. They will measure the expansion rate of their local cluster. They will see Andromeda and a few companions, and they will conclude reasonably that the universe is small, that it consists of a single galaxy or a small group of galaxies surrounded by endless empty space. They will have no evidence for the Big Bang, no cosmic microwave background to measure because the wavelengths will have been stretched beyond detectability. No distant galaxies to observe, no redshift data, no way to reconstruct the history of the universe. They will be cosmologically impoverished, cut off from the knowledge that we take for granted, because they will have been born too late, after the horizon closed, after the universe aged beyond the point where the evidence was still visible. We are lucky. We live in an era where the universe is still young enough that we can see its history written in the sky. The cosmic microwave background is still detectable. Distant galaxies are still visible. The expansion is measurable. We can trace the timeline back to the Big Bang and forward to the heat death. We have the data, we have the tools, we have the window, but the window is closing, slowly, imperceptibly, but inevitably, and there is nothing we can do to stop it. The shrinking horizon also has implications for the future of exploration. Even if humanity survives for millions or billions of years, even if we develop technology that allows us to travel at a significant fraction of the speed of light, there are places we will never be able to go, not because they are too far away, because the distance is growing faster than we can travel. If you left Earth right now in a spaceship traveling at the speed of light, which is physically impossible, but let us pretend, you could reach any galaxy within the current event horizon. Barely. But anything beyond that is unreachable. You would fly toward it forever and never get closer. The space between you and the destination would be expanding faster than you could cross it. You would spend eternity chasing a horizon that recedes faster than you approach. The galaxy would fade from view as its light redshifted into invisibility, and you would drift through an ever emptier void, alone, with no way to turn back because the expansion is symmetric. Every direction leads away from everywhere. This is not science fiction. This is the actual structure of the universe we live in. There are real galaxies, real places, real regions of space that we can observe right now but will never reach, and the number of unreachable places is growing. Every year, more galaxies cross the boundary. Every year, the reachable universe shrinks, and every year we are left with less. Not because the universe is getting smaller, because it is getting bigger, faster than we can keep up with. Faster than light can keep up with. Faster than anything can keep up with. Space does not care about speed limits. Space can expand as fast as the equations say it expands, and the equations, driven by dark energy, say it is expanding faster and faster. The only regions that will remain accessible are the ones bound together by gravity. The local group, the small cluster of galaxies that includes the Milky Way, Andromeda, Triangulum, and a few dozen smaller companions. These galaxies are close enough that their mutual gravity overpowers the expansion of space. They are not receding from each other, they are orbiting each other. Andromeda is moving toward us. It will collide with the Milky Way in about 4 billion years. The two will merge. The combined galaxy, sometimes called Milkomeda or Milkdromeda, will be the largest structure in our observable universe, and eventually it will be the only structure. Everything else will have receded beyond the horizon. The universe, from our perspective, will consist of a single giant elliptical galaxy surrounded by darkness. Observers in that distant future will look out and see nothing. No neighboring galaxies, no distant clusters, no cosmic web, just stars. And when those stars burn out, just darkness, an endless empty void stretching in all directions with no hint that anything else ever existed. That is the fate the cosmic event horizon is writing. Not an explosion, not a collapse, a slow, quiet fade out, as the lights go out one by one and the universe empties. The process will take hundreds of billions of years, longer than the current age of the universe many times over. But it is already underway. Galaxies are already crossing the horizon. Photons are already failing to make the journey. The separation is already happening, and it cannot be stopped. Some physicists have proposed that the event horizon is the most important boundary in cosmology, more important than the edge of the observable universe, because the observable universe is just a limit on what we can see. The event horizon is a limit on what we can ever interact with. It defines the causal structure of space-time. It separates the universe into regions that can affect each other and regions that cannot. And that distinction is absolute. There is no technology, no trick, no clever workaround that lets you send a signal beyond the event horizon. The laws of physics forbid it, not because we do not know how, because the geometry of space-time makes it impossible. Information cannot travel faster than light, and light cannot cross a gap that is growing faster than light can travel. The math is simple. The conclusion is final. Once something crosses the horizon, it is gone. And yet the universe beyond the horizon is still there. That is the part that feels wrong. We are not talking about regions that ceased to exist. We are talking about regions that are still real, still physical, still full of matter and energy and structure. But they are invisible to us, forever. We are living in a universe where most of what exists is hidden, not hidden behind a veil we might one day pull back, hidden behind a horizon we can never cross, a boundary written into the fabric of space-time itself, and that boundary is moving closer every year, swallowing more of the universe, cutting us off from more and more of reality, until all that is left is a tiny island of space surrounded by an infinite ocean we can never see. This is the cosmic horizon, the point of no return, the edge beyond which light cannot reach us, and we cannot reach anything else. It is not a wall, it is not a barrier, it is a consequence of expansion, a geometric inevitability, a feature of living in a universe dominated by dark energy, and it is permanent. There is no escape, no refuge, no second act. The universe is pulling itself apart, and the further apart it gets, the more of it we lose. The observable universe grows as new light arrives, but the reachable universe shrinks as galaxies recede, and eventually the reachable universe will be so small that it will contain only the local group, a few dozen galaxies, a few trillion stars, out of a universe that once contained trillions of galaxies and more stars than anyone could ever count. All of it still there, all of it still real, and all of it invisible, lost beyond a horizon that closed before we could reach it. The night sky will go dark, not all at once, slowly, galaxy by galaxy, one light at a time, each one fading as the last photons that will ever reach us arrive, and no new ones follow. Redshifted into the infrared, then into radio waves, then into wavelengths so long they become undetectable, and then nothing, just darkness. The stars in our own galaxy will still shine, for a while. But stars do not last forever. They burn out, die, collapse into white dwarfs or neutron stars or black holes. New stars will form from the remaining gas, but eventually the gas will run out, star formation will stop, the last stars will burn out, and then even our own galaxy will go dark. Black holes will persist for trillions of years, but eventually even they will evaporate through Hawking radiation, and then there will be nothing. No light, no structure, no heat, just a cold, dark, empty void, expanding forever into a future so distant and so empty that it barely qualifies as a future at all. That is what the cosmic event horizon is telling us. Not that the universe will end, that it will fade, slowly, inevitably, taking most of itself with it into a darkness we will never penetrate. And the only thing we can do is watch it happen, measure it, map it, record it while we still can, because the time when the universe was observable, when the evidence was still visible, when the sky was still full of light, is not permanent. It is temporary, a brief window in cosmic history, and we are living in it, right now, before the horizon closes, before the lights go out, before the universe becomes a lonelier, darker, emptier place than it already is. This is the fade-out, the great recession, the moment when the cosmos begins its long, slow retreat into isolation, and there is nothing beyond the horizon to save us. No outside to escape to, no larger structure to fall back on, just the universe, expanding, accelerating, leaving us behind, one galaxy at a time, until all that remains is the memory of a sky that used to be full of stars, and even that memory will fade, because in the far future there will be no one left to remember, no observers, no civilizations, no eyes to look up at the darkness and wonder what used to be there, just space, stretching forever into nothing, and the horizon will have won. But the horizon is not the only boundary we face, because while the cosmic event horizon marks the limit of what we can see and touch within this universe, some physicists have begun to ask a different question. Not what is beyond the horizon in space, but what is beyond the universe itself. Not in the sense of an outside, we have already established that does not exist, but in the sense of other universes, other bubbles of space-time, other regions where the laws of physics might be different, where the constants might vary, where the Big Bang happened separately, disconnected from ours, unreachable not because of expansion, but because they are fundamentally separate structures, a multiverse. And if that sounds like science fiction, it is worth remembering that 50 years ago, dark energy sounded like science fiction too, and now it is 68% of the universe. So maybe, just maybe, the horizon is not the end. Maybe it is just the edge of our bubble, and beyond it, not nothing, but everything. Infinite variations, infinite possibilities, a multiverse so large that our entire observable universe is just one tiny patch in an endless foam of spacetime. That is the idea, and whether it is true or not, it is where the conversation goes next. The night sky will go dark. That is where we left off. The cosmic event horizon closing in, galaxies slipping beyond reach, the universe emptying out as space stretches faster than light can cross it. A slow, quiet fade out into isolation. No escape, no refuge, no outside to run to. Because the universe is not inside anything, it is the only thing. And asking what is beyond it is like asking what is north of the North Pole. The question breaks, not because we lack the answer, because the question itself does not make sense. Outside is a concept that only exists within space, and space is the universe. You cannot step outside it. You cannot point beyond it, because beyond is a direction that requires space to define it, and there is no space outside space. That is the answer, that is the boundary, that is where the map ends, except maybe it is not. There is an idea, a strange, elegant, and deeply unsettling idea that has been circulating through theoretical physics for the better part of a century. It does not give you an outside in the way your brain wants. It does not provide a container that the universe sits inside. But it offers something almost as strange, a redefinition of what the word universe actually means, a suggestion that what we have been calling the universe, the totality of everything, might actually just be one piece of something vastly larger. Not larger in space, larger in scope. A structure so immense that our entire observable cosmos, all 93 billion light-years of it, all 2 trillion galaxies, all the stars and planets and gas and dark matter and dark energy, all of it is just one bubble in an infinite foam, one pocket in an endless landscape, one outcome in a branching tree of possibilities. The idea has a name. Physicists call it the multiverse. And if it is real, then the question of what is beyond the edge of the universe has an answer after all. Not nothing, not an outside, but everything. Infinite versions of reality, infinite variations on the laws of physics, infinite universes stacked alongside ours, unreachable, invisible, and utterly indifferent to whether we believe in them or not. The multiverse is not a single idea, it is a family of ideas, a collection of related but distinct proposals that all share one common thread. The suggestion that our universe is not unique, that the Big Bang was not the only Big Bang, that the laws of physics we observe, the constants we measure, the particles we detect are not universal, they are local, specific to this region of reality. And elsewhere, in other bubbles or branches or pockets of existence, things are different. The speed of light might be faster, gravity might be stronger, the electromagnetic force might not exist at all, or maybe the differences are smaller. Maybe elsewhere there are versions of you reading a slightly different version of this sentence. Or maybe the differences are so extreme that matter as we understand it cannot exist. No atoms, no chemistry, no stars, just empty void or pure radiation or something we do not even have words for. The multiverse does not pick one of these options, it includes all of them, every possibility, every variation, every configuration of physical law and initial condition that mathematics allows. all of it happening simultaneously, not in different places, in different realities, separate, disconnected, and completely unable to affect one another. The strongest version of the multiverse comes from a theory called eternal inflation. It was proposed in the 1980s by a Russian physicist named Andrei Lindade, building on earlier work by Alan Guth. Inflation is the idea that the universe underwent a period of exponential expansion in the first tiny fraction of a second after the Big Bang. Space expanded so fast that regions which were once close together were flung apart faster than light could travel between them. The entire observable universe today, everything we can see, was once a region smaller than a proton. And then inflation happened. Space stretched. Distances exploded. And by the time inflation ended, a fraction of a second later, the region had grown to the size of a grapefruit, or maybe a galaxy, or maybe much larger, depending on whose model you trust. That is standard inflation, the theory that most cosmologists accept because it explains several otherwise puzzling features of the universe: why space is so flat, why the cosmic microwave background looks so uniform, why the universe is so large. Inflation solves all of that, and the math works. The observations fit. The theory is solid. Eternal inflation takes it one step further. Linda pointed out that if inflation can start, it might not stop everywhere at once. In some regions, inflation ends, space stops expanding exponentially, matter and energy condense. A universe forms. Our universe. But in other regions, inflation continues. Space keeps stretching, and within that still inflating region, quantum fluctuations randomly cause small pockets to stop inflating. Each pocket becomes its own universe, its own Big Bang, its own separate bubble of space-time, with its own laws, its own constants, its own history, and the process never stops. As long as there is inflating space, new pockets keep forming, new universes keep budding off, forever. That is eternal inflation. Not one Big Bang, an infinite cascade of Big Bangs. A fractal structure where every universe is surrounded by inflating space that spawns more universes which are themselves surrounded by more inflating space. A never-ending process that has been running for eternity and will continue running forever. The multiverse is not something that might exist. Under eternal inflation, it is inevitable. If inflation happened once, it happened everywhere, and it is still happening, right now, out there, beyond the edge of our bubble. New universes are forming, new Big Bangs are igniting, and none of them will ever communicate with ours because they are causally disconnected, separated by inflating space that expands faster than light can cross it, exactly like the galaxies beyond our cosmic event horizon, except instead of losing galaxies, we are losing entire universes. This is called a level 2 multiverse. And it is the version most cosmologists take seriously because it is a direct prediction of eternal inflation. You do not have to add new physics. You do not have to invoke anything exotic. Inflation already exists. Eternal inflation is just inflation that does not stop. And if that is true, then the universe we live in, the observable universe, is one bubble in an infinite foam, a pocket where inflation ended, a region where space stopped stretching long enough for matter to condense and galaxies to form and stars to ignite and planets to cool and life to evolve. But the foam is still out there, the inflating space is still producing new bubbles, and each bubble is its own universe, its own separate reality, with no connection to ours. Here is where it gets stranger. In a level 2 multiverse, the laws of physics are not universal, they are local, specific to each bubble. The reason comes from string theory. String theory proposes that the fundamental constants of nature, Things like the speed of light, the strength of gravity, the mass of the electron are not fixed. They are determined by the shape and size of extra dimensions that we cannot perceive. There are many possible shapes, hundreds, thousands, maybe 10 to the 500th power, depending on whose calculation you trust. Each shape corresponds to a different set of physical constants, a different version of physics. In our bubble, the extra dimensions settled into one particular shape. That shape gives us the constants we measure, the universe we observe. But in other bubbles, the dimensions settled into different shapes, different constants, different physics. Some of those universes might be similar to ours, slightly stronger gravity, slightly weaker electromagnetism. Life might still be possible, stars might still form, but most of them would be radically different. Gravity so strong that matter collapses immediately into black holes, or so weak that nothing ever clumps together. Electromagnetism so powerful that atoms cannot hold together, or so feeble that chemistry never happens. Most bubbles would be sterile, lifeless, hostile to any kind of structure. We live in a bubble where the constants are tuned just right, not because someone designed it that way, because there are infinite bubbles and we can only exist in one of the rare ones where the constants allow life. That is called the anthropic principle, the idea that the universe looks fine-tuned because if it were not fine-tuned, we would not be here to notice. In a multiverse, fine-tuning is not a mystery, it is a selection effect. Of course, we live in a bubble where life is possible. We could not exist anywhere else. Level 2 solves the fine-tuning problem, but it does so at a cost. Because if the laws of physics are local, if the constants vary from bubble to bubble, then physics is no longer about discovering universal laws. It is about mapping the landscape of possibilities, figuring out which constants are possible and which are not. And that is a much harder problem. Some physicists find this idea liberating. The multiverse explains why the universe is the way it is without invoking a designer or a cosmic accident. Others find it deeply unsatisfying, because if anything is possible, then nothing is explained. You cannot predict what the constants should be. You can only say they could have been different. And that feels like giving up, like admitting that physics has reached the end of what it can explain. The constants are what they are because if they were not, we would not be here. Full stop. No deeper reason. No underlying principle. Just anthropic selection in an infinite multiverse. Some find that answer elegant, others find it a cop-out. But level 2 is not the only multiverse. There is another version, stranger, more radical, and in some ways more disturbing. It is called the level 3 multiverse, the quantum multiverse, and it comes from quantum mechanics, specifically from an interpretation of quantum mechanics called the many worlds interpretation. Most people know quantum mechanics as the theory where particles do not have definite positions until you measure them, where an electron can be in two places at once, where the act of observation changes the outcome. That is the Copenhagen interpretation, the version Niels Bohr and Werner Heisenberg developed in the 1920s. It works, it makes predictions, it matches experiments, but it has a problem. It requires a collapse. Before you measure a particle, it exists in a superposition, a state where all possible outcomes are happening simultaneously. Then you measure it. The superposition collapses. One outcome becomes real, the others vanish, gone, as if they never existed. The problem is that no one knows what causes the collapse. The equations do not describe it. The collapse is added by hand, an extra rule that says when you look at a quantum system, something happens that is not described by the math. That bothered a lot of physicists. It still does. In 1957, A physicist named Hugh Everett proposed an alternative. What if there is no collapse? What if the superposition never ends? What if every time a quantum measurement happens, the universe splits? One branch where the particle went left, another branch where it went right. Both branches are real, both continue evolving, but they are separate, decoherent, unable to interact. You, the observer, split too. One version of you sees the particle go left, another version sees it go right. Both versions are equally real. Both think they are the only version. Neither can communicate with the other. The superposition does not collapse. It branches, and every quantum event, every interaction, every moment, splits the universe into more branches. Trillions upon trillions of branches every second. An infinite tree of parallel realities where every possible outcome happens. That is the many worlds interpretation. And if it is true, then the multiverse is not just other bubbles beyond the horizon. It is other versions of this universe, other timelines, other histories, branching off at every quantum event, all of them happening simultaneously, all of them real, and all of them completely inaccessible to one another. Level 3 is controversial. Many physicists reject it outright. Not because it does not work, the math is fine, the predictions match experiment, but because it feels absurd. Every time you flip a coin, the universe splits into two branches, one where it is heads, one where it is tails. Every time an atom decays, the universe splits. Every time a photon passes through a beam splitter, the universe splits. The number of branches is unimaginably vast, and growing exponentially, faster than any number you can name. Some physicists embrace this. They say the many worlds interpretation is the simplest version of quantum mechanics because it does not require an ad hoc collapse rule. The equations just run. Everything that can happen does happen, in some branch, somewhere. Others say it is the least simple interpretation because it requires an infinite number of unobservable universes. You are multiplying entities beyond necessity, violating Occam's razor, creating a multiverse to avoid a single unexplained collapse. The debate has been running for 70 years, no resolution in sight. Both sides have good arguments, neither can prove the other wrong. Because by definition, the branches cannot interact. You cannot send a signal from one branch to another. You cannot observe the split. You can only infer it from the math. And different physicists draw different conclusions from the same equations. Level 3 does not give you an outside either. It gives you parallel realities, other timelines, other versions of now. But they are not somewhere else in space. They are everywhere, overlapping, decohered, happening in the same place but in different quantum states. You cannot travel to them, you cannot see them, you cannot affect them. They are as unreachable as the bubbles in level 2, maybe more so. Because at least with level 2, you can imagine, in principle, that if you traveled far enough and fast enough, you might reach another bubble. With level 3, there is no direction to travel. The other branches are not out there. They are here, in a different quantum state, separated by decoherence rather than distance, and decoherence is absolute. Once two branches split, they never merge, never interfere, never communicate. The separation is permanent. Then there is level 1, the simplest multiverse. The one that requires no new physics at all. Just space, infinite space. If the universe is infinite and current measurements suggest it might be, then somewhere out there, far beyond the observable universe, far beyond the cosmic event horizon, far beyond anything we could ever see or reach, there are other regions, other patches of space. And because space is infinite and matter is finite, and there are only so many ways particles can be arranged, eventually the patterns repeat. Somewhere, impossibly far away, there is another galaxy that looks just like the Milky Way, another star that looks just like the Sun, another planet that looks just like Earth, another version of you, reading these exact words, not because of quantum branching, just because in an infinite universe, every possible configuration happens and happens again and again, forever. This is level 1, the infinite space multiverse, and it does not require inflation or quantum mechanics or string theory. It just requires space to go on forever, which it might. We do not know. The universe could be infinite, or it could be finite but unbounded, like the surface of a sphere. Current data cannot distinguish between the two, but if it is infinite, then level 1 is real, and there are infinite copies of you out there, some identical, some slightly different, some radically different, all of them real, all of them equally you, and all of them completely unreachable because they are beyond the cosmic event horizon. Light from them will never reach us. Signals from them will never arrive. They are as lost to us as the galaxies that have already receded beyond the boundary. Except they are not separate universes. They are part of this universe, just very, very far away. Level 1 does not answer the question of what the universe is expanding into. It just says the universe is already infinite. It was always infinite, even at the Big Bang. The Big Bang did not happen at a point. It happened everywhere. Infinite space was always infinite. It just got less dense as it expanded. That sounds contradictory. How can something infinite get bigger? The answer is that infinity is not a size, it is a property. An infinite space that doubles in size is still infinite. The distances between objects increase, but the total extent was infinite before and infinite after. Level 1 does not give you an outside. It gives you more inside, infinite inside. And somewhere in that infinity, far beyond anything we will ever observe, there are other observers, other civilizations, other versions of this exact moment, all of them thinking they are unique, all of them wrong. And then there is level 4, the strangest of all, proposed by a cosmologist named Max Tegmark in 2003. Level 4 says that every mathematically consistent structure corresponds to a real universe, not just universes with different constants or different initial conditions, universes with fundamentally different mathematical rules, different dimensions, different logic, different definitions of what space and time even mean. If a mathematical structure is self-consistent, Tegmark argues, then it exists somewhere, in some sense, as a universe. This is the mathematical universe hypothesis. And it is not about physics, it is about mathematics. The idea is that physical reality is not just described by math, it is math. The universe is not made of particles or fields or spacetime. It is made of mathematical relationships, numbers, equations, structures, and any structure that is logically consistent has the same claim to existence as the one we happen to live in. We live in a universe described by the mathematics of quantum field theory and general relativity, but there are other mathematical structures, other axioms, other rules, and each one corresponds to a different level 4 universe, utterly alien, unimaginably strange, and completely real in the only sense that matters, mathematical existence. Level 4 is too abstract for most physicists to take seriously. It borders on philosophy, maybe crosses the line. But Tegmark defends it by pointing out that if mathematical structures are real, and physics has spent centuries discovering that the universe is mathematical to its core, then why should our particular mathematical structure be the only one that exists? What makes our universe special? Why should the axioms of quantum mechanics and relativity be the only axioms that correspond to reality? If math is real, and it seems to be, then all of math is real. And all of math includes structures we have never thought of, geometries we cannot visualize, logics we cannot follow, all of it existing somewhere in the space of all possible mathematical structures. Level 4 is the ultimate multiverse. It includes everything, every possibility, every configuration, every version of reality that can be described by any consistent set of rules. And it does not care whether you can observe it, because observation is a feature of our universe, not a requirement for existence. The multiverse, in all its forms, does not give you an outside. That is the first thing to understand. It does not solve the problem of what the universe is expanding into, because even if there are infinite other universes, they are not arranged in space. Level 2 universes are separated by inflating regions, but the inflating regions are still part of spacetime. They are not outside the multiverse. They are between the bubbles, like the dough between raisins in a rising loaf of bread. The dough is still part of the loaf. Level 3 universes are not in different places. They are in different quantum branches, same location, different state. Level 1 universes are just distant regions of this universe, and Level 4 universes are not in space at all. They are in the space of mathematical structures, an abstract landscape where distance has no meaning. None of them provide an exterior. None of them answer the question of what reality is inside, because reality is still not inside anything. The multiverse just expands the definition of reality. Instead of one universe, many. Instead of one set of laws, many. Instead of one history, many. But the totality, the full multiverse, whatever that includes, is still not in anything. It is still the only thing. The map has gotten bigger. The territory has not changed. There is still no outside. And here is the uncomfortable part. The multiverse is unprovable, by definition. If other universes are causally disconnected from ours, if no signal can pass between bubbles, if quantum branches cannot interfere, if level 4 structures exist in a purely mathematical sense, then there is no experiment that can confirm they are real. You cannot observe them. You cannot measure them. You cannot interact with them. The multiverse is a consequence of theories we already accept. Eternal inflation, quantum mechanics, the mathematical nature of physics. But the multiverse itself is not a prediction you can test. It is a feature of the theory, a side effect. And some physicists argue that makes it unscientific. If you cannot test it, it is not physics, it is philosophy. Or worse, theology. A belief system masquerading as science. Max Tegmark disagrees. He says the multiverse is no different from other unobservable entities in physics. You cannot observe an electron directly. You infer it from its effects. Same with black holes. Same with dark matter. You do not see the thing itself. You see what it does. And the multiverse, Tegmark argues, is the same. You cannot see other universes, but you can see the consequences of the theories that predict them. Inflation explains the flatness and uniformity of our universe. Quantum mechanics explains every experiment ever done at the atomic scale. String theory, if it is correct, unifies gravity with the other forces. And all three theories predict a multiverse, not as an add-on, as an inevitable consequence. If the theories are right, the multiverse is real. If the theories are wrong, the multiverse goes away. You are not testing the multiverse directly, you are testing the theories, and the multiverse comes along for the ride. Other physicists are not convinced. Paul Steinhardt, one of the founders of inflation theory, has become one of its harshest critics. He argues that eternal inflation makes physics untestable. Because if anything can happen in some bubble somewhere, then nothing is ruled out. You cannot make predictions. You cannot say this should happen and this should not. Every possibility is realized, every constant is sampled, every law is tried, and that means the theory explains everything by explaining nothing. George Ellis, a cosmologist who worked with Stephen Hawking, goes further. He says the multiverse is not science because science requires observations, and the multiverse by construction is unobservable. You can speculate about it, you can calculate what it would look like if it existed, but you cannot prove it is there, and you cannot prove it is not there. The multiverse is immune to evidence, and that, Ellis argues, disqualifies it from being a scientific hypothesis. It is a philosophical idea, interesting, maybe even true, but not science. The debate has been running for decades, no resolution in sight. Both sides have PhDs, both sides publish papers, both sides teach at top universities, and both sides think the other side is missing the point. The multiverse is either the most important idea in modern cosmology or the most dangerous, a natural consequence of successful theories or a warning sign that physics has gone off the rails and the data cannot settle it, because the data is all from this universe, our bubble, our branch, our patch of space. We have no access to the others, no window into the multiverse, no way to check if it is real. We can only follow the math and see where it leads. And the math, depending on whose version you trust, either predicts a multiverse or allows for one or says nothing about it at all. Take your pick. So does the multiverse provide an outside? No. Not in the sense your brain wants. It does not give you a container. It does not give you a surrounding void. It does not give you a place where the universe is expanding into. What it gives you is a new word. Universe used to mean everything, the totality of existence. Now, in a multiverse framework, universe means our bubble, our branch, our patch. And the totality is the multiverse, all the bubbles, all the branches, all the patches, together. And that totality is still not inside anything. It is still the only thing. The boundary has not moved. It has been relabeled. You thought you were asking what is beyond the universe. Now you are asking what is beyond the multiverse. Same question, same answer, nothing. Because beyond is a concept that requires space, and space, all of it, every version, every bubble, every branch is the multiverse. There is no outside. There never was. The multiverse does not solve the problem. It just makes it bigger. And yet the multiverse changes something. Not about the structure of reality, about the scope of what exists. If the multiverse is real, then our universe is not special. It is one among many, maybe one among infinite. The laws we observe are local. The constants we measure are contingent. Things could have been different, and somewhere they are different. That is a profound shift. For most of human history, we thought Earth was the center of everything. Then we learnt it was just one planet among many. Then we learnt our galaxy was one among billions. Then we learnt the observable universe was just a patch of a much larger, possibly infinite space. And now the multiverse is telling us that even the full universe, the whole thing, infinite or not, is just one bubble in a larger structure. One branch in an infinite tree, one solution to the equations among countless others. We keep zooming out, and every time we do, we find that what we thought was everything is just a piece of something bigger. The multiverse is the latest zoom out, and it might not be the last. But here is the thing, the multiverse does not make the universe less mysterious, it makes it more mysterious. Because now you have to explain not just why this universe exists, but why any universe exists. Why is there something rather than nothing? Why does the multiverse exist instead of not existing? And those questions do not have answers, not scientific answers, not yet, maybe not ever. Because the tools of science are built to explain things within the universe, cause and effect, observation and prediction, experiment and theory, all of those require time and space and physical law. And at the boundary of existence, where you are asking why existence itself is a thing, those tools stop working. You are outside the domain where science applies, not because science has failed, because you have reached the edge of what science can describe, the edge where physics becomes philosophy, where questions about what is turn into questions about why. And why does not have a mechanism. It does not have an equation. It just has the question, and the question sits there, unanswered, maybe unanswerable, staring back at you like a mirror, reflecting your confusion onto itself. The multiverse is a possible answer to what is beyond the edge of our universe. But it is not an answer to what is beyond the edge of everything, because everything, even if it includes infinite universes, is still something. And something raises the question of why there is not nothing. And that question does not go away. It does not get solved. It just gets postponed, pushed further out, into a realm where words start to fail and concepts start to blur, and the only honest answer is that we do not know. We might never know. And the recognition of that limit, that boundary where understanding ends, is where the conversation has to go next. We have traveled 46 billion light years. We have traced the expansion of spacetime back to the Big Bang and forward to the heat death. We have watched galaxies recede faster than light can chase them. We have measured the acceleration driven by dark energy. We have confronted the cosmic event horizon, the boundary beyond which light will never reach us. And we have asked the question that will not go away. What is the universe expanding into? And the answer, the one that physics gives us after a century of observation and theory and measurement, is nothing. Not nothing as in empty space. Nothing as in the concept does not apply. The universe is not expanding into anything because there is no outside. Space is not a container, it is the thing itself. And asking what it is inside is like asking what is north of the North Pole. The question sounds reasonable until you realize it is trying to use a concept that only makes sense within the framework it is asking about. You cannot step outside space because outside is a spatial concept. You cannot ask what happened before time because before is a temporal concept. And you cannot ask what the universe is expanding into because into requires a destination, and there is no destination. There is only the universe expanding, stretching, creating more space as it goes, not filling a void, becoming more. That is the answer. And if you are like most people, that answer does not satisfy you. It feels like a dodge. Like scientists are refusing to answer the question because they do not know. But the truth is harder than that. The truth is that the question itself is broken, built on an assumption that does not hold, the assumption that reality is the kind of thing that can have an outside. It is not. Reality is self-contained, complete, the only thing. And recognizing that, truly accepting it, requires a shift in thinking so fundamental that most people never make it. Because making that shift means letting go of the idea that the universe is a place, a location, a region of space sitting inside something larger. It is not. The universe is space, all of it. And space does not sit inside anything, because sitting inside is a relationship that requires space to define it. The framework cannot be inside the framework. The map cannot be inside the map. And once you realize that, once it truly lands, you are left with a conclusion that is equal parts beautiful and terrifying. The universe is all there is, and we are stuck inside it, not trapped, not imprisoned, just contained by the structure of reality itself. And that structure has limits, boundaries not in space but in understanding, places where the questions we can ask exceed the answers reality can provide. And that is where we are now, at the edge, not the edge of the observable universe, the edge of what we can know. Physicists do not like admitting this. The entire project of science for the last few centuries has been built on the idea that the universe is comprehensible, that nature follows rules, that with enough time and enough data and enough clever thinking, we can figure out how everything works. And that project has been astonishingly successful. We mapped the genome, we split the atom, we sent probes to the edge of the solar system and landed robots on Mars. We detected gravitational waves from colliding black holes 1 billion light-years away. We built telescopes that can see galaxies as they existed when the universe was less than 500 million years old. We measured the expansion rate of the cosmos to within a few percent. We catalogued 2 trillion galaxies. We determined the age of the universe down to 100 million years, 13.8 billion. Give or take, that is not a guess, that is a measurement, precise, reproducible, confirmed by multiple independent methods. The tools of science work, the equations predict, the experiments verify, the theories hold, and the overwhelming success of that process has created a kind of faith, not religious faith, scientific faith, the belief that every question has an answer, that every mystery can be solved, that the universe is not just knowable, but eventually fully knowable, that there are no walls, no limits, no places where understanding simply stops, and then you ask what the universe is expanding into and the walls show up. Not because physicists do not have an answer, they do. The universe is not expanding into anything. Space is expanding. That is the answer. The problem is that the answer does not feel like an answer. It feels like a restatement of the problem. Because your brain, wired by evolution to navigate a world of objects and containers and boundaries, keeps insisting that if space is expanding, it has to be expanding into something. That is how expansion works. Everything you have ever seen expand did so by occupying space that was already there. A balloon fills a room, a puddle spreads across pavement, a city grows into the countryside. Expansion is always into, always filling, always occupying, and the universe, according to physics, is not doing that. It is just becoming more, and your brain does not have a category for that. No mental model, no intuitive grasp, just a sense that something is being left out, that the explanation is incomplete, that there has to be more to the story. There is not. This is the terrifying part. Not terrifying in the sense of scary monsters or existential dread. Terrifying in the sense of confronting a boundary you did not know was there, a limit on what human minds can visualize. Cosmologists can describe the expansion mathematically. The equations work. General relativity predicts it. Observations confirm it. The framework is solid. But describing something mathematically is not the same as understanding it intuitively. You can write down the equation for a 4-dimensional hypersphere. You can calculate its volume. You can prove theorems about its curvature, but you cannot picture it. Your brain does not have the wiring. 3 dimensions are the limit. Add a 4th spatial dimension and visualization fails. Not because you are bad at math, because the human brain evolved to navigate 3-dimensional space, and it cannot construct mental images of geometries it has never encountered. The best you can do is analogies, projections, shadows of the real thing cast into a space you can comprehend. A hypercube rendered as a rotating wireframe. A tesseract flattened into 2 dimensions. Useful, informative, but not the thing itself. Just a hint, a glimpse, a representation that loses something essential in translation. The expansion of the universe is the same. You can describe it. You cannot visualize it, not accurately, not in a way that captures what is actually happening. Because what is actually happening is that space itself is stretching, and space is not an object. It is not a thing you can picture sitting somewhere doing something. It is the framework that makes picturing possible, the stage where mental images take place, and you cannot step outside the stage to look at it from the outside, because outside the stage there is nothing, no view, no perspective, no place to stand. The best you can do is analogies, balloons, rubber sheets, raisin bread rising in an oven, all of them useful, all of them misleading, because all of them are objects expanding into space, and the universe is not an object expanding into space, it is space expanding. And that distinction, small as it sounds, is the difference between something you can visualize and something you cannot. Physicists deal with this all the time. Quantum mechanics is full of concepts that cannot be visualized: superposition, entanglement, wave function collapse. You can write the math, you can calculate probabilities, you can predict outcomes to 10 decimal places, but you cannot picture what is happening, not really. Niels Bohr, one of the founders of quantum mechanics, reportedly said that anyone who is not shocked by quantum theory has not understood it. Richard Feynman, one of the greatest physicists of the 20th century, said that nobody understands quantum mechanics. Not nobody as in a few people are confused. Nobody as in the theory works perfectly, and no one has any idea what it means. The equations describe reality, but the equations do not explain reality. Not in the sense of providing an intuitive picture, just a set of rules that match observations. And that gap between what we can calculate and what we can comprehend is where the terror lives. The recognition that understanding has limits, that some things are true without being visualizable, that the universe operates according to principles our brains are not equipped to grasp. The expansion into nothing is one of those things. You can accept it, you can work with it. You can use it to make predictions and test hypotheses and build models of cosmic evolution. But you cannot make it make sense in the way that everyday experience makes sense, because everyday experience is built on assumptions that do not hold at cosmic scales. You assume objects exist in space. You assume space is static. You assume distances are fixed. You assume cause and effect flow forward in time according to rules you can trace. All of that is true locally, at human scales, in the environment where your brain evolved. But step outside that environment, look at the universe as a whole, and the assumptions break. Space is not static. Distances are not fixed. Cause and effect get tangled. And the comfortable intuition you rely on to navigate the world stops being a reliable guide to what is real. This is not a failure of physics. It is a feature of reality. The universe is not required to make sense to you. It is not required to fit into categories your brain finds comfortable. It is required only to be consistent, to follow rules, to behave in ways that can be described mathematically. And it does that perfectly. General relativity describes the expansion of spacetime. Quantum mechanics describes the behavior of particles. The Standard Model describes the forces and fields that govern matter and energy. All of it works. All of it predicts. All of it matches observation to extraordinary precision. The fact that none of it makes intuitive sense, the fact that you cannot picture it, is a problem with intuition, not with physics. Your brain is a tool that evolved to help a primate navigate a world of trees and predators and social hierarchies. It was not designed to understand the structure of spacetime at cosmological scales. The fact that it can do so at all, even mathematically, is remarkable. The fact that it cannot do so intuitively is not surprising. It is expected. And yet, the lack of intuitive understanding creates a kind of discomfort, a sense that something is missing, that the map is incomplete. David Hume, the 18th century philosopher, pointed out that all human knowledge comes from experience. We build mental models by observing patterns. Cause follows effect. Objects persist over time. Space is three-dimensional. Gravity pulls things down. Fire is hot. Water is wet. We generalize from specific instances to universal rules, and that process works beautifully as long as the rules we are generalizing hold everywhere, but they do not. Gravity does not always pull things down. Ask an astronaut. Fire is not always hot. Ask a chemist about cold flames. Space is not always three-dimensional. Ask a string theorist. And the assumptions we built from experience, the ones that feel obviously true because we have never seen them violated in everyday life, turn out to be approximations, local truths, rules that hold in the specific environment we evolved in, but break when you push outside that environment. And the universe does not care. It is not trying to be comprehensible. It is just being itself, following the equations, evolving according to the laws of physics. And if those laws produce outcomes that human brains find baffling, that is a human problem, not a cosmic one. Some physicists find this liberating. The universe is stranger than we imagined, more complex, more subtle, more beautiful in its mathematical elegance than any picture we could have drawn before we started looking. Others find it unsettling. Brian Greene, a physicist and author who has spent his career explaining relativity and quantum mechanics to general audiences, has described the experience of working on these problems as a kind of cognitive vertigo. You follow the math is clear, the conclusions are unavoidable. And yet the conclusions describe a reality so far removed from everyday experience that you can hold them in your mind only provisionally. You can work with them. You cannot live in them, not mentally. Your intuition keeps pulling you back to the world of objects and containers and boundaries. And every time you remind yourself that the universe does not work that way, it feels like stepping off a ledge, not into emptiness, into something stranger, a space where the rules are different and the map no longer matches the territory. And the scariest part is not that the universe is strange. The scariest part is that it might be fundamentally unknowable. Not unknowable in the sense that we lack the tools or the data. Unknowable in the sense that the structure of reality itself places limits on what can be understood. Gödel's incompleteness theorems, proven in the 1930s, showed that any sufficiently complex logical system contains true statements that cannot be proven within the system. You can add axioms to capture those statements, but then new unprovable truths appear. There is no final, complete, consistent system. Mathematics, the language we use to describe the universe, has built-in limits. Truths that are true but unprovable. And if math has limits, then physics, which is built on math, inherits those limits. There may be questions about the universe that are true but unanswerable, not because we are not smart enough, because the structure of logic itself does not allow an answer. And if that is the case, then the project of science, the mission to understand everything, is doomed to incompleteness. Not through failure, through necessity. Some physicists reject this idea. They argue that Gödel's theorems apply to formal systems, not to physical reality. The universe is not a logical system. It is a thing, a real concrete thing, and things can be measured, observed, tested. There are no unanswerable questions, only questions we have not answered yet. Give us time, give us better instruments, better theories, better math, and we will get there. Every mystery that has ever been solved was once considered unsolvable. Lightning was the anger of gods until we understood electricity. Disease was divine punishment until we discovered germs. The structure of matter was unknowable until we built particle accelerators. The history of science is a history of boundaries being crossed, limits being exceeded, mysteries being solved. And there is no reason to think we have reached the final limit, the edge of what can be known. We are just at the edge of what we know now, and the edge will move. It always has, maybe, but maybe not, because the edge we are facing now is different from the edges we have faced before. We are not asking how stars shine, or what atoms are made of, or whether space is curved. We are asking what the universe is, and whether the question even makes sense. We are asking what it means for something to exist, and whether existence requires a cause. We are asking why the laws of physics are what they are, and whether the laws could have been different. We are asking whether the constants are tuned or random, whether the multiverse is real or a mathematical fantasy, whether the universe is finite or infinite, whether time had a beginning or has always been. And those questions, all of them, are pushing at the boundaries not of knowledge but of language, of concepts, of what it means to ask a question, because every question assumes a framework, a context, a set of rules that make the question meaningful. And when you ask what is outside the universe, or what came before time, or why there is something rather than nothing, you are asking questions that may not have a framework, that may not be meaningful in any sense that allows an answer. And that is the terrifying truth. Not that the universe is big or old or strange, that it might be in some fundamental way beyond us. That the gap between what we can describe mathematically and what we can understand intuitively is not a gap we will eventually close. It is a gap built into the structure of minds trying to comprehend the thing they are part of. You are made of atoms. Atoms follow quantum mechanics. Quantum mechanics does not make sense. You are the thing that does not make sense trying to make sense of itself. And maybe that is a task that cannot be completed, not because you are not trying hard enough, because the task is paradoxical, self-referential, circular, the map trying to contain itself, the eye trying to see itself, the program trying to debug its own code. And maybe some tasks are just impossible, not difficult, impossible, ruled out by the structure of logic itself. Some people find that conclusion depressing. If there are questions we can never answer, then why bother asking? If the universe is fundamentally unknowable, then why study it? If the edge of understanding is real and permanent, then science has already lost. It has run into a wall it cannot climb, a boundary it cannot cross. And the project is over. We have learned what we can learn. The rest is silence. But that is the wrong way to look at it. Because the boundary is not at the edge of the observable universe. It is not at the cosmic event horizon. It is not even at the limits of what our instruments can measure. The boundary is conceptual, philosophical, and philosophy does not stop when science does. It starts. The recognition that some questions might be unanswerable does not close the conversation, it opens it. Because once you acknowledge that the universe might be stranger than you can imagine, you stop trying to force it into categories it does not fit. You stop demanding that reality makes sense on your terms. You start asking different questions, not what is the universe expanding into, but what does it mean for space to expand? Not what came before the Big Bang, but what does it mean for time to have a beginning? Not why do the constants have the values they do, but what does it mean for a constant to have a value? You shift from asking questions about the universe to asking questions about the questions, meta-questions, questions about the structure of inquiry itself. And that shift, uncomfortable as it is where the deepest insights come from. Because the universe does not owe you an explanation. It does not owe you comfort. It does not owe you answers that fit into the frameworks you built to navigate a world of rocks and rivers and other humans. It just is. And your job, if you are brave enough to take it on, is not to make the universe make sense, It is to make sense of the fact that the universe does not make sense, to find meaning not in the answers but in the search, not in the destination but in the journey, not in solving the mystery but in living with it. And maybe that is the real lesson, the thing cosmology has been trying to teach us for a century. That the universe is bigger than we thought, stranger than we imagined, older than we expected, and fundamentally beyond our ability to fully grasp, not beyond our ability to describe. We have equations. Not beyond our ability to measure. We have instruments. Beyond our ability to comprehend in the way we comprehend ordinary objects, because the universe is not an ordinary object, it is the totality, the everything. And everything does not fit inside the categories we use to describe parts of everything. You cannot visualize it, you cannot analogize it, you cannot reduce it to something simpler. You can only describe it, mathematically, precisely. And then sit with the discomfort of knowing that the description is accurate but the understanding is incomplete, and maybe always will be. That is the terrifying truth. Not that the universe is expanding into nothing, that we have reached the edge of what minds like ours can know. And the edge is real, and permanent, and unavoidable. Not because we are stupid, not because we are not trying, because the structure of reality is such that some questions do not have answers, some mysteries do not have solutions, some boundaries cannot be crossed, and the recognition of that, the acceptance of it, is not defeat, it is humility. The humility to recognize that the universe is not required to make sense to you. That understanding is not a right, it is a gift. And the gift has limits, and those limits are written into the fabric of existence itself. You are a pattern of atoms organized in a way that allows the universe to think about itself, and that is remarkable, and also insufficient. Because the universe is bigger than any pattern of atoms can hold, stranger than any mind can picture, deeper than any theory can capture. And the best you can do is acknowledge that, accept it, and keep looking anyway. Not because you will find all the answers, because the search itself is the point. The universe is 46 billion light-years in radius. It is 13.8 billion years old. It is expanding faster than the speed of light at large distances. It is accelerating under the influence of dark energy. It has no edge, no outside, no container. It is not inside anything. It is the only thing. And it is, in all those ways, beyond us, beyond intuition, beyond visualization, beyond the frameworks we built to make sense of a world that is vastly smaller and simpler than the cosmos we find ourselves in. And that is okay. You do not have to understand it. You just have to accept that it is real, that the equations describe it, that the observations confirm it, and that the lack of intuitive sense is a feature, not a bug. The universe is not broken because you cannot picture it. Your picture is broken because it was built for a different scale, a different context, a different reality, and the universe does not care. It is doing what it does, stretching, expanding, evolving, creating more space as it grows, not into anything, just more. And if that does not make sense, that is fine. It does not have to. The universe is not here to make sense, it is here to be, and you are here to watch and wonder, and occasionally, if you are very lucky, to catch a glimpse of something true, even if you cannot fully understand it, even if it terrifies you, even if it sits at the edge of language where words start to fail and concepts start to blur, and the only honest response is silence, not the silence of defeat, the silence of awe, the recognition that you are standing at the boundary of the knowable, looking out into something vast and strange and beautiful, and utterly, completely, forever beyond your grasp. And that is not a reason to stop looking. It is a reason to keep going, because the universe is not going to explain itself, but it will let you watch, and in the watching, in the questioning, in the endless search for understanding that never quite arrives, you find something deeper than answers. You find meaning, not in what you know, in what you are willing to live without knowing. And that, more than any equation or observation or theory, is the real edge of everything. The place where science becomes philosophy, where knowledge becomes wonder, where understanding becomes acceptance, and where the terrifying truth, the one that has been waiting at the end of this journey all along, finally lands. You are small, the universe is vast, and most of what exists will remain forever beyond the horizon, not because it is hidden, because the structure of space-time itself has drawn a line you cannot cross. And on the other side of that line is everything, and you are here. And that is both the most terrifying and the most beautiful fact in all of cosmology. You are here. The universe is there. And the gap between the two is measured not in distance, but in the limits of what it means to be a mind trying to grasp the infinite. And the infinite does not fit. It never did, and it never will. And that is okay, because the search was never about fitting the universe into your head. It was about expanding your head to hold as much of the universe as it can, and then recognizing, with humility and awe, that no matter how far you expand, there will always be more. More universe, more mystery, more questions, more unknown. And that more is not a wall, it is an invitation to keep looking, to keep wondering, to keep asking, even when the answers do not come. Even when the questions stop making sense, even when the only response is silence, because the silence is not empty. It is full of everything you will never know, and everything you will never stop trying to understand. And that is the edge of everything, not a place, not a boundary, a recognition that the universe is bigger than you, stranger than you, more than you, and always will be. And that is not a failure, it is the point. So here we are, standing at the edge of a question that has no answer, staring into a structure so vast and so strange that the best minds in physics can describe it but cannot make it make sense. The universe is not expanding into anything, it is expanding into itself, creating more space as it goes, not filling a void, becoming more. And that sentence, simple as it sounds, is the boundary, the place where intuition breaks, where visualization fails, where the comfortable categories you use to navigate the world stop applying, because the world is not the universe. The world is a tiny patch of space-time where gravity holds things together and expansion does not matter. Step outside that patch, look at the cosmos as a whole, and the rules change. Space stretches, distances grow, galaxies recede faster than light, and none of it requires an outside, because outside is a concept that only makes sense inside. That is the answer, and it is also the limit, the edge of what human minds can know, not because we lack the data, because the question itself is trying to use a framework that does not extend beyond the thing it is asking about. You cannot step outside space to see what space is inside. You cannot step outside time to see what came before. You cannot step outside existence to ask why existence is a thing. The map ends, not at the cosmic horizon, not at the edge of the observable universe, at the boundary of language itself, where questions stop having answers, not because the answers are hidden, but because the questions are asking for something that does not exist. And maybe that is the most honest thing physics has ever told us. The universe does not owe you comfort. It does not owe you answers that fit. It just is, expanding, stretching, evolving according to equations that work perfectly and make no sense. And you are inside it, a pattern of atoms trying to understand the whole, knowing you never will, searching anyway, because the search is the point, not the arrival. The journey. And the journey does not end at the edge of everything. It ends at the recognition that there is no edge, just more universe, always more, forever out of reach, forever worth chasing. That is the edge of everything, not a place, a realization that the question you started with was the wrong question, and the right question has no answer. And that is not a failure. It is the most profound truth you will ever encounter. The universe is not a mystery to be solved. It is a reality to be lived in, wondered at, measured, described, and ultimately accepted as something bigger than understanding, stranger than comprehension, and utterly, completely, forever beyond the grasp of any mind that tries to hold it. And that is exactly as it should be,